technological evolution for nearly 70 years. And it's important for us to sort of look at that history and see where we are and how we could go forward. So the earliest mention of the word artificial intelligence is actually about 70 years old. In 1955, John McCarthy coined the term artificial intelligence, and the focus of that community was symbolic AI, mimicking human intelligence, and that sort of stream started in the mid 50s. And it's sort of we are sort of living through it in some ways. There was another stream that started even earlier than 1950s, okay? And it sort of had a major development in 1957, which was perceptron, which could be viewed as the beginning, the seed of the deep learning revolution, right? Now, it's very interesting. Today, we are living in the AI revolution, which is driven by deep learning. But at that time and back in 1955, these two directions were intensely competing with each other, right? One, AI was focused on mimicking human intelligence. And the second one was focused on building a paradigm of computing that was inspired by brain. They had completely different objectives, and they were competing. And literally, we could sort of say that the people working in the upper direction literally wrote a paper. Marvin Minsky wrote a paper which sort of killed the funding and directions in the deep learning, in the neural network computing. Now, that AI, the upper field, continued over a period of 35 years. I've sort of seen the history from 50s to 85. It had multiple ups and downs, and it culminated in the late 80s. Some of you may remember the term expert systems. The world was sort of going to be driven by expert system. It was sort of one of the highlights. But somebody may also remember the declarative AI and procedural AI and the logic programming, the fifth generation computers. Again, a lot of you who are young would not remember it, but in the computing in the 80s and 90s, that was sort of the key thing to do, right? So those are the kinds of things sort of were happening back then. In the neural network world, the direction sort of came up in the 50s for a little bit, then it went underground, then it came back again in the mid 80s with the second surge of neural networks. It stayed up for about 4 years and then went down, right? So this is what happened in the 35 years. Of course, developments kept happening. It's very interesting to know that today, one of them has taken the name and the other one is driving the direction, right? But whatever you're seeing today for the last 12 years or the last few years was driven and sustained by what happened in the middle for about 23 years. Okay? And the focus entirely in the middle was on big data analytics, big data, being able to solve big problems, large variety of data sets, and large variety of applications. And that sort of created another stream. And during this time, nobody was calling it AI or machine learning or neural networks. And it sort of culminated at the end in 2012 with the big data initiative by the White House. And that sort of led the field of data science, right? And you can sort of see that even the scientific community, you see the two covers of Nature and Science. One of them says data, the other says big data. That means already by 2008 and 2009, the wider scientific community was beginning to see there's a lot of value in being able to analyze large data sets from different angles. This big data initiative in 2012 was preceded by a McKinsey report in 2011, which sort of said that there is trillions of dollars in savings that can be obtained by analyzing large data sets. Now, both of these developments that happened 35 years before and the 23 years after that led to where we are. It turned out in 2012 also is the year where a whole bunch of things started happening. Okay? And one of them, the first event, was this marquee event, AlexNet wins ImageNet challenge. And that was sort of the point at which, for the first time, all the people who were working in quote unquote the neural network community for the previous 50 years were able to show that they have some algorithms that they can actually do dramatically better than what the computer vision community and pattern community has been trying to do for the previous 50 years and was using the network. And they were able to do it because of, again, confluence of data and computing and algorithms. Algorithms they had, but the data and computing had not mocked up to it. And it was a major event looking back, but it was also noticed by only a small number of people. But then quickly after 2012, a series of things happened. every few years, something major would happen. And of course, we are here today that, AI is everywhere, right? The next thing that happened was in 2013, there was a methodology called self-supervision learning in the context of languages. Word2Vec is sort of the short form of it, which sort of dramatically revolutionized how you could model languages. And just to give you an idea, the idea is so simple that you take, so there were two directions that were sort of been driving the research in AI for a very, very long time, which one of them is being able to recognize images. If you look at something, can you figure out what's happening there? It's human capability. And the second thing is language, being able to understand or communicate in languages. So language modeling research has been going on for a very long time, and yet has very limited successes until this point. And in 2013, when this new algorithm was developed, just a year after the first revolution, or the AlexNet demonstration, which was you take the words in any language, let's say in English language, you want to represent them as numbers, as vectors. If you can represent them as vectors in a way that they may have some conceptual meaning, it could be very useful. And by using this Word2Vec self-supervision approach, which requires absolutely very simple algorithm, but extremely large amount of data and computing, you're able to convert words into vectors that they have such a strong semantics meaning that you can take the vector for king, subtract the vector for man, add the vector for woman, and you get queen. You take the vector for Paris, you subtract the vector for France, you add vector for Rome, and you get Rome, and you get Italy. So these are the kinds of understanding you could do. It immediately revolutionized everything that was happening in the language community. That is, these things happened literally by 2015, the entire language modeling community had gone off from the standard approaches over to deep learning. Then very quickly after that, in 2016, AlphaGo beats HumanGo champion, again, a major milestone. It's a major milestone because in 1956 is also about 70 years ago, one of the founding fathers of computer science, Herbert Simon, made a prediction that now that we know how to write algorithms for playing games for which we know the rules, alpha, beta, and the like, it's going to be only a matter of time before computers will be the best champions or the most expert players. And he predicted within 10 years, the computers will beat the heck out of anybody. 10 years passed, nothing happened. 20 years passed. The first time a computer was able to beat a chess champion was 40 years later in 1996 with a massive supercomputer built by IBM, just not too far from here. A supercomputer that had to really play 200 million moves in a second to get there, right? But then forward 20 more years in 2016, AlphaZero, simply by giving the rules of the game and a lot of computing power, was able to play the game by itself, learn enough that now once it's learned it, it can just beat anybody and then do a actually much, much better job, right? And again, the methodology for that came again from this first 35 years of what happened in AI, right? So what I'm trying to say is that there are different kinds of things came together at different times, but when they came together, they actually did absolutely remarkable thing. Then 2018, AlphaFold solves protein folding. Immediately, the scientific community woke up and they saw something dramatic here. 2022, of course, ChatGPT came in, everybody sort of got shook up. And then pretty soon, every scientific community in every walk of life started thinking, how can we use this technology for their own uses? Okay? So this is where we are at this point. So it's clear to us as a scientific community that AI is poised to disrupt science. There is no question in anybody's mind of that, right? It also should be clear to people who are following the history that everything that you're using today, from ChatGPT to neural networks, to transformers, to anything that you sort of have seen, all of them that you're aware of came out of the communities that were working on computer vision and language modeling. Okay, but there is an increasing feeling sinking even within the AI community that the next revolution in AI will be driven by a wider class of scientific problems, right? And if you look at the modeling of chemicals, designing new materials, new drugs, modeling the ecology of the planet. These are problems that they're much different in nature than being able to look at an image and figure out what is in it, or being able to model the languages. Right? So there are very, very rich problems. And that sort of is the feeling that's been brewing for a long time. 3 years ago, exactly 3 years ago, one of our big conference in big data, the KDD conference, was held in Washington, D.C., and they had a day-long panel in which they had one track in which the people from federal government, all the agencies come and have different sessions, sort of discuss the opportunities. And one of the sessions was devoted to NSF, and I chaired that session. And as a part of the discussion, this point sort of came up, that is, what would be the next frontiers in AI? That was 3 years ago. And that led to a series of workshops, 2 workshops. One of them was held at the headquarters in NSF in Arlington, Virginia in March of 2023. And the second was held right here in this room about a year ago. And the purpose of those 2 workshops was just exactly this notion, that is, how could we drive the next revolution in AI that would help us with scientific problems, and vice versa? How would the focus on scientific problem would help enable the next revolution in AI? So this is sort of that was the goal of these. And the second workshop report was published in the Spring and Nature's Artificial Intelligence Journal. This is the copy. And again, the most relevant part of that report, perhaps, is this figure, which is sort of capturing the structure of this report, in which we sort of talked about 1 year ago as to how generative AI is being used in science. And at that time, 1 year ago, this room was full and with people from different scientific disciplines, and quite a few people were sort of talking about the standard LLMs being adopted directly as it is to use for scientific applications. And there was a beginning of people, the smaller number of people, who were beginning to think about domain-specific foundation models for scientific research. Right? So those are the 2 different groups that this report talks about. It was captured in the snapshot. It talks about kinds of scientific problems that are ripe for generative AI. That is, what are the kind of entirely new problems that you could sort of solve that you could not have imagined solving before. Learning with multimodal and multi-scale data, being able to transfer information from one context to another one, building digital twins in ways that you could not have imagined before, experimental design, and things like that. And then it sort of talked about what is currently missing in the current state of the art in generative AI, and how we could potentially fix those gaps, right? And how do we build this next generation of ecosystem for generative AI for science? And again, this is it's about a report about a dozen pages, and it has a lot of details. And this report actually informed the structure of this meeting to a great extent. Now, so the main goals for this meeting as we go forward are, number 1, to set the stage by tracing GenAI's foundations and emerging trends, continuing on the previous workshop. Highlight opportunities for advancing GenAI methods and testbeds inspired by unique demands of science and engineering. So far, much of the development that are happening are driven by the standard benchmarks people have in computer vision and language modeling. When one of these big corporations come back and say, my LLM is doing better than something else, they use the standard benchmark that they have. They probably have nothing to do with the kinds of problems that you're trying to solve in your respective disciplines. Identify pathways for future breakthroughs in GenAI through deeper integration of scientific principle and domain expertise. There is an opportunity here to fundamentally advance the frontiers of AI in ways that we could not have imagined before. Always remember that for the last 70 years, is the 2 problems of computer vision and pattern recognition and language modeling that have driven the entire research. And then, again, that brings us to the 4th point, that we want to anchor our discussions in high-impact scientific domains, designing materials, manufacturing, agriculture, environmental science, life sciences, and healthcare, these kind of problems. And more importantly, as we look forward, we develop a shared agenda for research that inform future methods, benchmarks, investment priorities in GenAI4Science. Okay? And of course, this workshop has been under planning for many months, but the America's AI Action Plan was just released about a couple of weeks ago. And it was so striking to see as to how much of this report's uh, focus is connected to a previous report and, of course, the agenda of this meeting, which is defined by the previous report. And I just took some quotes out of this report. This is the if you go on Google, any search engine, just type America's AI Action Plan, you'll find this article. There's also a QR code here that you can use to get there. And science itself will be transformed by AI. So there's a recognition now everywhere, right? It's not something that, we were talking 3 years ago, that people know that science will be transformed by AI, but AI will enable new innovations for which terminology does not exist. And I say that because if I go back, things like in-context learning, the foundation models, the generative AI, none of these were on our tongue of people who have been working in the field for 70 years. I know if you go 10 years before, generative AI would mean something very simple to you, generative models, Bayesian models, building, given a bunch of samples, you generate a distribution. You couldn't think of what you would do with this very much more, right? So as we are building new constructs, new algorithms, new ways of thinking, we are beginning to think as a community completely new thing. And I think we should not underestimate that. We should not underestimate one of our peers, one of our students in the lab would come up with something that would just be so surprising. And I say that because one of the major developments that I mentioned to you for deep learning, Word2Vec, happened at Google. For example, the chief scientist of Google, Jeff Thien, he came and gave a talk here just 2 months ago. He was our commencement speaker, and he also gave a sort of talk in the college. And he started his presentation by the copy of his honors thesis that he did in 1990 at the University of Minnesota under my supervision. Okay? And he sort of said the TensorFlow, which enabled everything, all of this revolution they're talking about, all of the elements are directly connected to what I was thinking as a student, as an undergraduate student, right? 30 years ago, right? So it's a beautiful demonstration of how simple ideas can change the world, right? So we should be fully prepared to accept that somebody in our class, somebody in the cohort, they could be the next the next person who will be revolutionizing the field, right? So just as generative AI represented a paradigm shift, future breakthrough may similarly transform what's possible with AI. I think this is the most exciting part. We don't know what's coming, even though we are trying to push it forward as go forward. And the other quote that I loved very much in this report, it comes from the America's AI Action Plan, and there was a sentence there. This is an industrial revolution, an information revolution, and a renaissance all at once. See, Renaissance happened 500 years ago. Industrial revolution happened 250 years ago. Information revolution as an internet happened in our eyes about 30 years ago, right? And now you're sort of seeing something that's so powerful that it's bringing all three of them together in a way that is going to change everything. So we cannot underestimate what we are in for it, right? This America's Action Plan also had a whole bunch of policy recommendations. And if you go back and read it, they will have some text and the policy recommendation. And each of the policy recommendation actually even specified many agencies that are responsible for it. And it actually is very intriguing and very satisfying for us that the 5 agencies that we have represented here in this room actually are very frequently highlighted in the report. I could almost like, you guys have the burden of sort of moving this forward. So I'm really looking forward to, of course, the federal panel that will be coming tomorrow. But you can sort of see an investment in new and transformative paradigms that advance the capabilities of AI looking forward. The next bullet is extremely important. Very specific focus, very direct focus on domain-specific efforts in individual disciplines like healthcare, energy, agriculture, and which is sort of reminding us that if you keep using LLMs as they exist, maybe you're limiting yourself. You got to build something that's specific to it, because the underlying technology that allows you to build these LLMs actually is so powerful that you can go into a specific domain and you can do wonders potentially. And that's, of course, going to be the focus of a lot of the panels here. Advanced interpretability and robustness support the development of science of measurement and evaluation, test beds, and scientific researchers to release data sets. So these are all the kinds of things that were reflected in the previous year's report, and of course, all the focus of this action plan. So with that, I just want to sort of get you started on the rest of the program. We are starting a little bit late here, but we'll adapt. We'll skim on the break a little bit, and then maybe the lunch would be a little shorter. But we have a fantastic set of sessions planned here for you. We wanted to start this meeting with a session on giving a backward and forward-looking view on generative AI. What are the foundations and what are the frontiers as we look forward from the vantage point we are at? And there are 3 speakers there, and they have prepared a beautiful set of slides and presentations. They're going to be talking right after me. After that, we have a panel moderated by Raja Acharya from NSF, focusing on GenAI methods and testbed. And then in the afternoon, of course, we have panels on ecology and agriculture, followed by some lightning talks by people from University of Minnesota and poster receptions. And then, of course, day 2 has a series of panels as well. So with that, let me stop here and invite Anuj Karpatne, who's going to give the first talk. There's a series of talks, right? All right. Thank you.
Let's just make sure the Zoom recording is working well. Let it change.
Share. The screen too, perfect.
And check
Oh,
if
two,
the
me
name-
too. Yep. I'll put them in. Yep. That's it. And then
All right, okay. All right. Thank you, Vipin, for the wonderful overview and introduction to this workshop. And welcome everyone to the opening session of the workshop on foundations and frontiers of generative AI in science and engineering. I'm Manish Karpatne. I'm from Virginia Tech, and I have the pleasure of co-presenting this opening session along with Aryan Deshwal from University of Minnesota and Jana Dofa from Washington State University. And all the slides that we will be going through have been collaboratively prepared over a series of sessions spanning several months with heavy contributions from Vipin Kumar. So the goal of this opening session is to, as Vipin mentioned, talk about the backward and the forward directions, right? To understand what is GenAI, what are the different variations of GenAI methods, what are their different origins, their emerging capabilities, their opportunities, and how they are impacting and are being influenced by problems in science and engineering. For the next 90 minutes, we'll be going in and out in subsets, covering different topics of GenAI. And we'll take breaks in the middle to stop for the questions. So there are 3 parts to this opening session. Part 1 is going to focus on introduction to GenAI. Part 2 is going to talk about emerging opportunities at the intersection of GenAI and reinforcement learning. And part 3 will talk about opportunities in advancing GenAI inspired by the needs in scientific problems. So with that, I can move ahead to the first part of the session, which is on introduction to GenAI models from the perspective of their origins, how they have been enabled by advances in deep learning, what are their differentiating characteristics, what are their emerging capabilities, right? And this is a talk that will be co-presented with Aryan. So we can start with a primary definition, right? What is GenAI, right? So at a very high level, we can think of the goal of generative modeling to build a distribution of data samples by learning this probability distribution P of X, where X are the data samples. And we would generally assume that X is high dimensional. For example, we are working in the space of generating images, text, code, and so on. Optionally, we may also have information about some conditioning variables Y, in which case we are interested in modeling the joint distribution of P, X, comma, Y. And in the modern era of generative AI, right, you have many different models that are out there, right, which are some listed over there. This is certainly not exhaustive. There are many others, but we'll work with this set. And in this talk, we'll go into more technical details of their origins and their differentiating capabilities. But before we do that, let's talk about what are the enabling, what are the different applications of GenAI. So the most standard or the most mainstream applications of GenAI is generating text, generating images, generating code, right? Applications that have been enabled by models like ChatGPT and other frontier foundation models. But in science and engineering applications, generative models can be used for many other applications, for many other use cases. For example, generating new molecules, generating new drugs, generating new materials, polymers. Right? Generative models have the capability to perform what-if scenario analysis. Right? What if we change the input forcings? How would it affect changes in the target variables? Or it can even help us generalize to novel unseen tasks, right? Which we'll get to very soon. And you can contrast these applications, these definitions from predictive or discriminative AI frameworks, where the goal is slightly different, where given some inputs, X, we want to predict target variables or response variables Y. Right? Y could be categorical, Y could be numeric, it could be structured as well. Right? Here we are mostly after learning the conditional probability, right? P of Y given X. And there is an entire suite of models that have been developed, ranging from decision trees to neural network models. And this is an area which has seen the most interest, especially in the early phases of deep learning. Right? They enable completely different applications. Right? We can classify objects in images. We can classify the sentiment in text. Right? Or in science, we can predict molecular properties, land covers. Right? And you can see how they contrast with the capabilities that GenAI models are enabling, right? Where we are not just making predictions on these data points, we are generating these data points. And historically, there has been a lot of contention between generative and discriminative models, right? Going to discussions comparing logistic regression models and Bayesian networks. In the classical frameworks of generative AI, the model structures were handcrafted or were assumed to be known, right? For example, in Bayesian networks. But in the modern era of generative models that we are seeing over here, listed as boxes, we are seeing a few key differences from classical generative models. The first major difference is that instead of using handcrafted or structures that are known a priori, we are letting the data drive the learning of these model structures. Right? So these are much more flexible than their historical counterparts. The second key difference is that this distinction between discriminative versus generative models has become quite blurred. Many of these generative models exploit discriminative objectives, discriminative architectures, right? But use them in novel ways to solve generative problems. Another key feature of modern GenAI models is they exploit some form of structure in the data. For example, the structure of space, the structure of sequences in text data. They exploit some form of regularity or continuity, right? And these three properties, these key differences, would keep on showing up in more detail as we discuss these models going forward. But all these developments that you're seeing in the middle box, right, haven't happened in vacuum. Right? They have been inspired by and enabled by developments that have happened across different research areas or schools of thoughts. Right? These can be viewed as the headwaters, right, that are leading to the river that is now generative AI. And this has been a highly non-linear journey, right, where these models have been inspired by developments from multiple origin pieces. Let's go through a few of these origin pieces in detail to understand where we are coming from. So if a major field that has contributed to modern GenAI approaches is, of course, Bayesian formulations, which have classical roots in directed and undirected graphical models. As I mentioned, the structures that they're using to model the probability distributions are handcrafted or are known. Right? And these have inspired methods, modern GenAI methods, such as VAEs, variational autoencoders, that employ similar probabilistic formulations. But there is a completely different area of research that has also contributed to GenAI methods, which is this entire space of autoregressive models, right, that use some portion of your data to predict the next portion. This can be rolled over in along the temporal dimension, tracing its roots in time series forecasting models like ARMA and ARIMA that are also autoregressive, to Bayesian formulations like hidden Markov models, to sequence-based models like LSTMs, RNNs, and more recently transformers. Right? And we also have autoregressive models going in space, right, where we take a portion of a spatial data and make predictions in the spatial directions, looking at spatial autoregressive models, Markov random fields, and so on. Right? These ideas are now living in modern generative AI architectures like GPTs, right, that would factorize the joint probability distribution that we are after as a product of conditionals using the chain rule. Another area that has contributed to GenAI is this framework of generative adversarial networks, right? That is inspired by adversarial optimization, where you have a generator and a discriminator that are pitted against each other, and they're both being trained jointly. We also have Nobel Prize winning methods such as restricted bolt span machines, RBMs, that have inspired recent advances in GenAI that go after the problem of modeling energy functions, right, which can be viewed as unnormalized probability distributions. Right? So rather than looking at exact probability learning, can we learn energies? And these ideas now live in score-based interpretations of modern GenAI methods, such as diffusion models. And in the later part of this talk, we'll go into more details about each of these models. But at this stage, we are just covering the conceptual roots. Another conceptual root of modern GenAI models is this entire space of latent space modeling, right, where we assume that the data lies on a lower dimensional manifold, right? Borrowing ideas from linear techniques such as PCA to non-linear methods such as autoencoder. And they have inspired techniques that now live in variational autoencoders. And finally, we have this this area of research in science on forward inverse modeling, right? Where the forward problem is to map some inputs to observed outputs, right? And the inverse problem is then to retrieve the inputs given the observations. Problems such as denoising, compressed sensing would fall in this category, right? And they have influenced advances like diffusion models, normalizing flows, in using very different architectures. So this just summarizes the different conceptual roots, right? The origins that have led to modern GenAI models. And each conceptual root has its own trajectory of how they have influenced modern GenAI frameworks. But progress in each of these trajectories would not have been possible, or would have happened at a very slow speed if it was not for key advances in the field of deep learning that have almost supercharged or turbocharged this entire GenAI revolution. These are listed here in blue. They are representation learning, self-supervised learning, context-sensitive learning, or the use of transformers. And their use is all-encompassing. So they cut across all the modern GenAI frameworks that are listed over here. So let's go through each of these advances and the historical timeline of advances, of developments in each advance one by one. So one of the key enablers of GenAI is this idea of representation learning, right? Which is central to the entire field of deep learning, right? Where the idea is to automatically extract features from raw data, from raw signals, as abstract representations in the hidden layers of a neural network. Right? This is different from using handcrafted features that had been the workforce in computer vision language modeling communities for a long time. It's different from designing specialized kernels that work for certain applications, or choosing sophisticated distance metrics. Right? In the era of deep learning, right, we are letting the data speak for itself and learn and get us to the right feature representations. And this entire field of representation learning has its origins back in perceptrons, right? And happened more than 70 years ago. It's one of the initial sparks of the deep learning revolution. And as Vipin mentioned, there has been several winters, several ups and downs in the field of deep learning. But one of the turbocharging moments for representation learning or deep learning in general was this AlexNet winning the ImageNet competition in 2012. And that led to several other developments in powerful predictive architectures like convolution neural networks, recurrent neural networks, solving vision and language problems. Many of these developments, these breakthroughs, were enabled by the availability of massive labeled data, right, that we were able to collect in computer vision through ImageNet, or we could scrape from the internet for language problems. But these advances were still restricted in the confines of labeled data. Right? In applications where you had lots of labeled data, we could see the success of representation learning. All of that changed with this second turbocharger of GenAI, which is the idea of self-supervised learning, right? Where we are moving outside the confines of labeled data to learn feature representations using ample availability of unlabeled data. So at their very core, these models that are being trained using self-supervised learning are still deploying discriminative or predictive architectures. But they have turned these predictive models on their head to leverage their prediction capabilities, but for tasks that do not need external supervision, right? Or are self-supervised, right? Leading to generative modeling capabilities. Again, this entire field of self-supervised learning has its origins in techniques developed more than 40 years ago. Right? If you go to the framework of autoencoders developed in the 80s, right? We were able to learn feature representations of data without the use of labels. Right? We also had frameworks such as Siamese networks that are exploring contrastive learning formulations. But the turbocharging event for the field of self-supervised learning, as Vipin mentioned, happened with the introduction of word-to-vec, right? Where when we were able to scale these models, right, on the internet scale text data, to see very interesting emergent properties appear when we looked at perturbations and transformations in the embedding space. This inspired many developments. For example, in the field of computer vision, right, we had a similar development of masked autoencoders, right, where you could mask a certain portion of the image and see if you can reconstruct that. Right? So there are different frameworks of self-supervised learning, and there's a tutorial link that goes into much more detail about these techniques. But some of these are reconstruction-based, where you want to apply techniques like autoencoders or masked autoencoders, or you could explore next word prediction tasks, where given the current tokens, you want to predict the next token. Or you can explore contrastive learning based methods with roots in Siamese networks, right? Where we are exploiting our information of how data points are distributed in the original space. If we have knowledge about their distances, can we use them to learn more meaningful feature representations? Now, notice that all of these techniques in self-supervised learning are exploiting some form of our knowledge of the structure in the data. That they're assuming that in the low-dimensional manifolds, right, there is continuity, there is regularity, right, there is smoothness. Right? And that point is important as we think of the next frontiers of GenAI. Right? What are the other forms of structure, of regularity that we can exploit to develop new self-supervised learning methods? The third turbocharger of GenAI is the framework of building context-sensitive architectures, right? Where the idea is at a high level that to make predictions on a certain point, I need to be aware of the context of the other data points that influence me. Ideas in this space go back to methods like k-nearest neighbors, right? Where you have a notion of your neighborhood or your context, to techniques like geographically weighted regression, Kriging, Gaussian process, and even methods such as Hopfield networks that are modeling interactions between different variables. The modern counterpart of context-sensitive architectures is transformers, right? Where the attentions are capturing the context in a much more flexible way that is completely learned from data, rather than using fixed or handcrafted structures of what is the context. For example, what is the right value of k, or what is the right distance function in the original space. Where for every token, for example, if I encounter the word it in a sentence, the model is able to understand what are the other tokens that are relevant to understand pronouns like it. So these are three of the key enablers of GenAI, and we're not going into details about each of these advances. But here is just a landscape of summarizing the different GenAI models that we see in the modern era, and how they have their roots in different conceptual areas. we can see that there's a lot of cross-pollination that has happened. Multiple conceptual roots that have come together to create the modern GenAI models. And there are also many untapped opportunities in creating hybrid formulations. Looking at more origins or historical roots to enable next advances. For example, can we combine the idea of autoregressive models with diffusion models, right? Bringing in forward inverse energy-based and autoregressive formulations. So with that, let me summarize with what we discussed. We talked about different GenAI models without going into details of any of them. We talked about their conceptual roots, their history, the backward direction, and the deep learning advances that have enabled them. But what remains to be discussed are the characteristics that differentiate these models, right? In a certain application, when should we choose diffusion over GPTs, and what are their emerging capabilities? And this is where I'll hand it over to Aryan.
Yeah, thanks, Anuj. Good morning, everyone. Welcome to UMN. Yeah, so I'm going to talk about some of these new GenAI methods that you see, what goes into them, what's the recipe, and also what are the new capabilities that are enabled by these methods. So rather than listing them one by one and going through slides, we were thinking maybe we could try to characterize these generative models along different dimensions. And we've listed these 5. And of course, like any list, this is not exhaustive, but we feel it is quite good enough to capture different trade-offs and assumptions that goes behind all these modern generative AI methods or models that we hear about. And also very useful to think about when we are thinking about a new application, for example. So some of them are quite easy to understand. For example, yeah, we care about the quality of our generated samples. What is the fidelity of generated samples? Sometimes it is easy to do that perceptually. Sometimes we can use proxy metrics to do that. We care about suitability to different data types, right? We have data types sometimes which are discrete in nature. Some data type are continuous in nature, different dimensions. We care about the cost of generating samples, right? We'll talk about some applications later where, for example, in digital twin applications, you don't want to wait for your generative model to generate a sample forever. And then there are 2 very key properties, which I'm going to go in a little bit more detail, which are really very big characteristic. At least the 4th one is a big characteristic of modern GenAI methods. So one of them is this ability to guide towards desired property, right? All of us here who are interested in some applications are not interested in just unconditional generation. For example, in molecule design or protein design, we're not just interested in generating any protein, but hopefully a useful protein with high activity for something, for a property or high property we care about. So really this characterization, this dimension is trying to ask this question, can we guide these models in an easy manner towards these good specific characteristics that we care about? And can we do that without retraining the generative model again and again as much as possible, right? And so this is really fundamentally having some accessible control knobs during our generation process. And I'm going to characterize the class of model that we talk about today along 3 categories. So a big class of models, which are the most popular right now, allow high controllability in a plug and play manner, where you can plug and play different types of characteristics you care about. Some of them are much harder to control, and some of them provide some medium level of controllability. Another dimension along which you can characterize different GenAI models is their ability to estimate the probability of a sample. This seems probably the most direct thing you would think about when you think about a generative model, but sometimes it is surprisingly not talked about a lot. But this is actually a very useful metric for apples to apples comparison across different types of generative models. So very similar to like when we think about supervised learning or discriminative AI, we talk about accuracy as a metric. Similarly, we can use the likelihood or the probability of samples. So for example, what do you do in standard machine learning? We have a held out set, we compute its accuracy, test set accuracy, and we see how well our model is doing. We can similarly compute the likelihood of a held out set to compare our different models. Unfortunately, I'm here to share the bad news. Not every model provides this probability in a very exact, tractable manner. So that's why this is a dimension. And we can also use this dimension, like this property for other downstream tasks like anomaly detection. So the categories along which this dimension we are going to talk about is whether models natively provide us exact tractable likelihood, or we have to somehow approximate the likelihood using some procedure. So along these 5 dimensions, I'm going to talk about the 3 most popular generative AI models that we all hear about today. And starting with GPT, our #1 model, I guess, where, as Anuj mentioned earlier, so GPTs or generative pre-trained transformers it's very nicely captured by this GIF, are autoregressive models, which means they generate sequences by predicting each element one at a time, where each prediction depends on all previously generated elements. And because we typically use transformers as the architectures, here that's why we call them GPTs, but they are underlying the model is the autoregressive model. So this is the characterization of GPTs along the 5 dimensions I talked about. Of course, we all use ChatGPT, so we do know that they provide very high quality samples, at least for natural language or text. The key assumption behind autoregressive models broadly is that they are applicable to data with a particular order in mind. And it turns out natural language, the way we create language, has a particular order, so which is great. Another nice thing about autoregressive models is that they are very nicely generalizable to variable length data. So for example, text is variable length, where typically how we represent an image is fixed size, right? So this is a good property to have of GPTs or autoregressive models generally. Unfortunately, generating samples from GPTs is relatively expensive because you need to generate samples step by step. And the controllability aspect, the 4th dimension, is quite nice because and I'm going to talk about this property in a lot more detail later, but we can literally pass instructions to GPTs and get responses for queries we care about, right? And one very nice thing about them is because of this ability to autoregressively factorize the probability distribution, we get exact tractable likelihoods. And that is why a lot of the time when you read, let's say, papers about language models, there is a metric people always talk about, which is perplexity. Perplexity is very much the likelihood, but turned into numbers, which is easy for us to understand, humans to understand. But perplexity is literally likelihood, and we can get it in exact tractable manner with autoregressive GPT models. The next very popular class of models right now, which is used for lots of domains, going beyond language in most domains out there, high dimensional domains, so images, videos, robotics, even lots of scientific domains, are what are called as diffusion models. And the key idea behind diffusion models is that they learn to generate data by trying to reverse this simple noise corruption process. So as you can see in this figure, there's a forward process where we're trying to gradually transform data, real data, into pure noise over many time steps. And the diffusion models, the key magic is in the reverse process where we try to denoise it to go back from noise to pure real data. And the key characteristic, if one message about diffusion model, if you want to remember, is the idea of iterative refinement. So unlike autoregressive models or GPTs, where errors can propagate much easily, here you have a chance because you are denoising over multiple steps. You have a chance to fix your mistakes sometimes. So this notion of iterative refinement is really central to these models, and that's why a lot of excitement along this class of models. And this is the characterization along the 5 dimensions for diffusion models. they provide very high fidelity of samples. And in fact, if some of you might know that the precursor of models in image modeling before diffusion models was GANs. And one big reason was diffusion models actually provided much more high quality samples when you look perceptually at images compared to even GANs. They are natively suitable for fixed length continuous inputs because the notion of denoising makes very natural sense for continuous inputs. Unfortunately, generating samples is again expensive because you're doing this iterative refinement step by step. They are highly controllable, and among the popular class of generative models today, I would say the reason diffusion models are all around us in so many applications is because of their precise controllability in a plug-and-play manner. So any property you care about, for example, just with a frozen pre-trained diffusion, you can just guide it separately without retraining it. And that has become their really, really big deal. And if some of you remember, when DALL-E came out, we were all impressed with images generated by provided text. That really the big deal about that is that you can guide image generation using text, which was not feasible that easy, for example, with GANs or other models earlier. They do not provide exact likelihood, so we have to approximate the likelihood for these models so that we can compare across different classes. So this is the 5 characteristics of diffusion. Another popular class of models is variational autoencoder. And the key idea behind them, as shown in the figure, is that you have 2 networks now where you learn a low-dimensional representation, this latent representation, from your original input by passing it through an encoder neural network. And then a decoder neural network tries to reconstruct the data from this latent input. And typically, this latent input is lower dimensional. So this is a key property of variational autoencoders, which is not there, for example, in diffusion and other models, is that you can convert from high dimensional spaces to low dimensional spaces. So that's why they are very frequently coupled with other class of models. For example, all the video generation models we see out there, Sora and others, use VAEs as the first step to go from the full pixel space of images to a relatively lower dimensional space and do diffusion in that latent space. And these class of models have actually been very popular in the last few years for molecule design problems because this latent space allows you some controllability and you can search in that space as well. And I'm going to talk about those applications later. So this is the characteristics along the 4-5 dimensions that we talked about. VAEs in the standard form have known to be not provide very high quality samples. And they are natively suitable, again, for fixed length continuous inputs. They provide very fast samples because it's just one pass through your decoder. So sampling here will be just passing after you have trained it. You just pick a point in the latent space and pass it through your decoder. So it's much more faster than other 2 classes. They provide some level of controllability by searching in the latent space. Again, they do not provide exact likelihood, so we have to use approximate procedures to compute this likelihood, this metric, which is very useful. So this is a summary of these GenAI methods, the popular classes at least, along these 5 capabilities. Now, like any list, I mentioned this, and I have to caveat because some of my friends would be working on and coming telling me, hey, but I can use my consistency model to sample a diffusion much more faster. I know about a diffusion language model. Yes, and we are all working on these problems, and this is an active research direction, but I think this is a good starting point, at least to characterize some of these trade-offs when we think about, when we read these papers, we can have these trade-offs in mind to differentiate between different classes which are popping up all the time. Now, as Vipin actually mentioned very nicely in the beginning, these are the classes of models which are very popular. So these are modeling approaches or algorithms. But there is one more key ingredient that goes into modern Gen AI, especially since GPT-3, like 2020, which is this aspect that these models, so these formulations, are also combined with increasingly large amount of data, large sizes of these deep neural networks to represent them, and they are trained on large computing systems. And as shown in this figure, so one aspect of this is that Now, when you're trying to train these large systems, and you probably take a 6 months or an year investment on training your fastest, so best generative model, you have to be careful about making that investment. So you want to make some observations about how would my performance be. And it turns out this is a very nice property of deep learning models, is that they have very predictable scaling properties, which means as you increase, as you can see in this figure, very famous figure of modern machine learning, if you increase the compute size, data set size, and parameter size, these models, the test performance, which is on the y-axis, tend to improve very predictably, which is very nice to have now, because you can train smaller models to try to see how is, and try to extrapolate these curves. But again, these are empirical observations, and the name laws is always a misnomer, but still these are very useful for engineering. And some of our systems colleagues will tell us how hard it is to train large-scale distributed systems. So I'm not going to belabor that point, but the one key ingredient that I'm going to talk about a little bit is the data aspect, right? So sometimes people think about it's a very commonly, oh, these models are trained on all the internet, but it's not just the quantity that matters. And a lot of what goes into, there is a lot of amount of effort that goes into curating the right amount of data to train these models. So which means both diversity and quality of the data also matters. So as an example, like this is a very famous PILE data set for language modeling. This is not just, for example, just random text, but also combines different forms, different domains, for example, code and other domains. And the mixture of these domains matter a lot for the final performance of these models. And as an example to show that data quantity alone is not enough, for example, this is a figure from trying to scale up protein language models on just evolutionary sequences where we are already seeing diminishing returns. So which means either we have to go beyond, maybe to metagenomics data sets and other data sets, or we have to think about other strategies. So data scaling is also a science, and we have to carefully think about that as well. But scaling done well, why we care about scaling is when scaling done well, we have seen examples that it leads to new emergent capabilities for which the model was not explicitly trained on. And this GIF shows very nicely, for example, for Google Palm model, when you increase the data set and the parameters, you get these new properties, new tasks that can be solved, which were not, the model was not explicitly solved, trained for. So really, the general recipe of modern GenAI is these combinations of new, better algorithms, right, or iterative refinement algorithms, but also thinking very carefully about the right way of scaling these different components. And now let me quickly talk about some of these new capabilities, why we are so excited about them. Of course, the biggest one is that we can generate new instances of high-dimensional object, right? Generating images and videos and language, we all use them in everyday life. But for scientific applications, generating proteins, materials, molecules, these are very impactful applications. And these are all high-dimensional combinatorial objects, which are much more harder to just search over without these tools, which is really nice. And code, I think this is sort of very nice to emphasize, especially for CS people, that program synthesis is still, I'm not saying it's solved, but is a very hard problem, which a lot of people have been trying to solve for a lot of time. But the fact that we can generate code is also a nice thing. The other aspect I sort of alluded it to in the characterization earlier is the plug and play guidance. We can steer these models towards properties we care about. For example, let's say protein models, we can steer towards high activity, let's say an enzyme for some high activity we care about, or molecules for, let's say, a drug property we care about, right? So I think that's another very important capability which is enabled, especially with these diffusion models. So it's much more easier to do compared to the previous generation. And this very nice aspect, which has been alluded multiple times already, is that now we can start thinking about generalizing to novel downstream. So the training is, I've talked about examples, this autoregressive modeling or iterative refinement. Once we train this giant model, I can then use it for lots of different tasks, downstream tasks, in a much more easier, efficient manner. And this is very important for sciences. Why? Because as most of us who's worked with science data sets, we've seen many times that there is a long tail of tasks that we want to solve. And all of them come up with these specialized data sets with their own unique variances. So standard machine learning or AI always had high difficulty solving some of these tasks. But I think this is at least an opportunity with some of these new models we can do that. And of course, one way to do this, there are two popular ways to do it. One way is the standard fine-tuning approach, where you update the parameters of the network, the deep neural network representing your model, with the new data set we care about. But because we talked about emergent capabilities, a very nice property and emergent capability of these models is you can also do without updating. You can also you can also use them for downstream tasks without updating the parameters, or this property of in-context learning. So we sometimes just pass instructions and models reply to us to do certain things, right? Or learning from a few samples. And this is really a key defining aspect of modern generative AI models. And this was actually the popular thing about GPT-3. GPT-3 was just scaled up model from GPT-2, but the big deal was this emergent capability of in-context learning. And this is also the capability, because we keep hearing about agentic AI systems. Agents have been studied in reinforcement learning and robotics forever, but the key capability is that now with in-context learning, we do not have to update our models when we get our observations, and we can use this property to learn on the fly. So that's why it is very important. And this capability, along with the other ones, has led us to the era of foundation models, right? We talk about all these big famous foundation models, Gemini, Cloud, ChatGPT, and lots of other vision language models, for example. And really all of these capabilities enable this modern era. And so just to summarize this part one of the talk, we have talked about the conceptual roots and the frontiers and what goes into modern Gen AI models. But what we have talked about till now is just about learning passively from observation, learning passively from data sets which is collected. At least I believe, and most people I think would agree, that intelligence and also problem solving there is a very big, another thing we need, which is exploration, active exploration. And that's where comes in reinforcement learning, and Jana Dopa is going to talk about that.
Okay. Right. Yeah, thanks for the nice introduction, both Anuj and Aryan. Great job. So my name is Jana, and I'm going to talk a little bit about what we can potentially look at some frontiers in terms of improving the capabilities of these Gen AI models. And reinforcement learning has been one of these recipes that actually enabled some of it. So I'll start off with some introduction to RL, and then I'll talk about some promising directions that could lead to some new capabilities in the context of science and engineering applications. So let's talk about the moment that we went from GPT to ChatGPT. And the main ingredient from GPT to ChatGPT, like Aryan was alluding to, was this reinforcement learning from human feedback. So the idea was that there were some prompts, then there were basically some responses, and you collect data from humans that would actually tell which response was better than an alternative response, right? So you collect a lot of such preference data, and then you use some sort of supervised learning to learn a reward model, and then you plug that reward model into a reinforcement learning algorithm to create this kind of capability. So that's called RLHF, which is in short, reinforcement learning from human feedback. And those of you who don't know about reinforcement learning, so this is one quick slide. So the main difference between reinforcement learning and standard supervised learning is that in standard supervised learning, you are given actually an answer to every problem, and you are trying to mimic that behavior. On the other hand, in reinforcement learning, you're not told what the right answer is. So the agent is in an environment, and the agent has to try some strategies or solutions to figure out which solutions are better. And that's the solution for a reinforcement learning problem is what is called a policy, which is at any given state, the policy would tell you what action or the decision to take. And the way it happens is it's kind of a trial and error process where the agent takes an action at a state, gets a reward or penalty for that action, and then it updates its strategy. So it is almost like learning by acting in that world. So to put that in context here, so what we do here is you have this LLM, and the LLM generates responses, and the humans provide feedback like thumbs up or thumbs down, where they give some feedback for which responses they prefer better, and you can use the standard RL on this. Now, when you take this to reasoning tasks, for example, I gave you a couple of examples here where there is a math word problem and also a programming problem where a prompt is given and the LLM has to generate the corresponding code. Even in these cases, if you have a computational verifier, which basically means that for the reasoning problem that you are trying to solve, you have a way to figure out whether the answer is correct or not. For example, in the context of code, you might have unit tests, and you can run the code on those unit tests and basically say, either give a Boolean binary signal where you say, well, this answer is correct. Or you say some numeric value, like, okay, it passed, so what fraction of the unit tests, and so on, right? So the computational verifier can actually is the supervisor signal that can help you improve these models on these reasoning tests. And there are many such examples like OpenAI O1, DeepSeek R1, Cloudase Extended Thinking. So these are all examples of these reasoning model. And I would say RL in generative AI is still very nascent. And I would like to argue in today's talk is that many science and engineering problems have some unique challenges compared to the kind of reasoning problems that I just showed you. And that should inspire new RL ideas. And that's what the focus of my talk is. And I'm going to start my talk with an inspiration from Marvin Minsky. Marvin Minsky is actually a very, very quotable person. He's a Turing Award winner. And in his book called Society of Mind in 1986, he said, intelligence is shifting the test part of generate test into generation. And throughout my talk, I'm going to talk about some ways we can actually realize this insight in the context of learning and reasoning in GenAI models. So the first direction is integration of knowledge. So if you kind of abstract out everything, all you can say is that given an LLM, it can generate some candidate hypotheses, right? So let's say there are some top K hypotheses. And ideally, what we want is that based on all the facts and knowledge that a domain scientist knows, every hypothesis that is generated in this top K should be consistent with those facts and prior knowledge, right? Otherwise, it's a missed opportunity. So the question is, how can we do that? So if you have such facts and knowledge written down, you can think about it as a black box procedure called knowledge verifier, where you put in all these facts and rules, and every time a hypothesis is generated, you pass it as an input to this knowledge verifier. And knowledge verifier could provide you a binary signal where it says, well, this hypothesis is consistent with my known facts and knowledge. Or it could give you a numeric signal where it says, well, it violates these many facts or existing rules. And that could be the reward function that could actually drive the training of these models. the second aspect is that even though you had a knowledge verifier, which actually provided the supervisor signal, you might still not be able to learn a model that will always be consistent with the knowledge. There is no guarantee, at least for some forms of knowledge. So in that case, what you can do is, even during your inference, right, you can actually put this knowledge verifier in the loop. As you generate, you can get feedback from this knowledge verifier, and you can update the reasoning strategy when you are generating these candidate hypotheses, right? So both at training and inference, you can do it to actually always generate these consistent hypotheses. There is one more idea that I wanted to actually touch upon, which could be very complementary to this other view, is if you think about all these reasoning and exploration that is happening, you can think about, okay, you can do the standard greedy decoding, and it might be fairly good. And only at some very fork in the road kind of decisions, if it gets it wrong, the errors can propagate and you can get very bad hypotheses. So you can actually use that insight to basically see, can you do some intelligent search around this greedy decoding or the greedy policy so that you can actually explore this large combinatorial space much more intelligently? And I'm going to just list a couple of papers here. Unfortunately, the first paper, actually, I consider it as a very, very good paper. Unfortunately, the community didn't pick up. It's called Choice Function Framework for Online Policy Improvement, although it's not written in the context of LLMs, but I think the ideas from that paper are actually very, very relevant for this. In fact, if you know about AlphaGo, I mean, they tried basically supervised learning, and the greedy policy initially was not good enough, and they had to wrap basically the Monte Carlo tree search around the greedy policy to the winning agent. And the other idea I would also touch upon is what is called limited discrepancy search. It's actually one of my own paper from my PhD work. And in fact, I was able to find, this was like before overleaf era, right? So I was actually very, very happy last night. I was able to find the PDF of this paper, okay? So this was a paper that I submitted to NIPS 2011. I mean, that's what NeurIPS was before. And my title was Learning to Search at Test Time for Classifier-Based Structured Prediction. So in fact, I would argue that this paper actually, or this line of direction, started the whole test time search. Unfortunately, the paper got rejected and we resubmitted, and it led to a lot of good research. So the second direction that I would argue is what is called adaptive experimentation. So all the successes that we have seen so far assumes that there is actually a verifier that can actually tell you what the right answer is, right? Whenever you actually generate a solution, whether it is the correct or not. But in lots of scientific applications, when you have candidate hypotheses, right, there is no computational procedure that would actually tell you whether this is the right material or what property it would have, unless you actually make that material and evaluate in a physical lab, right? And the reason, because these science applications, these experiments are actually expensive. They need to be conducted by humans, and they also consume physical resources. You cannot just use them as you have done in the traditional games or a computational verifier. So you have to be very, very careful about on what queries you want to actually find the answer. So you have to be very intelligent about it. And that's where the adaptive experimentation tools can be pretty useful. And it's actually a very unexplored area, even in the context of general LLMs, not just in the context of science applications. In fact, there is a new paper at Column which talks about the sample efficient preference alignment. And I'm actually very proud that it's actually written by one of my former students who is a postdoc in Stefano Ehrman's group at Stanford. And one thing that I would actually tell you, I was working on a AAI fellow nomination for Alan Fern this summer, and I was trying to kind of write, the impact of some of his RL research. And this was actually a paper written in NIPS 2012. This was actually my lab mate, Aaron Wilson. And at that time, there was actually a research program going on, like, okay, RL has been very, very popular in games, right? Where you can always reset and actually try many, many times. But when it comes to RL for humans or any kind of real world domains where you're kind of trying to design strategies where limited exploration is possible, you need to be sample efficient. And this paper talks about actually one search strategy called how do you get preferences from trajectory to learn policies in a more efficient manner through humans. In fact, I was actually trying to look at the RLHF paper to see if actually this paper was cited or not, but this is exactly the formulation behind the RLHF paper. Okay, so the point I was trying to make through this is that there are lots of good ideas in the literature, and if the community goes back beyond the last 5 years, I think you will find a lot of gold, and you can actually try to reuse in the context of these ideas. So the other thing, adaptive experimentation can be useful is, there is a lot of excitement about discovering new rules and new laws and new knowledge, right? And both from, passive data, which was already collected, but also doing some new experiments to validate them. I think you can use adaptive experimentation in a more efficient manner to learn such rules. And then you combine these new rules that are discovered into the knowledge integration framework to further improve the capabilities of these LLMs. The third direction I'm going to talk about is there is a need to improve the reasoning capabilities of these Gen AI models. So you might see a lot of papers which kind of talks about, okay, in spite of all these capabilities, the LLMs actually don't do well on lots of reasoning and planning tasks. So I'm actually listing a couple of things. So there was a recent paper from DeepMind, and Subbarao Kamampati, who is a faculty member at Arizona State University over the last 5-6 years, he has written a whole bunch of papers which kind of talks about why LLMs still cannot plan or reason. And one key limitation of these tools is that they cannot perform deductive reasoning, right? Which is a very, very basic reasoning mechanism all humans use, like the ability to derive new facts and knowledge from existing facts and rules, which I would argue it's a fundamental aspect of intelligence. Through just forward chaining, you can actually get all of this. But, you can see LLMs as doing some sort of case-based reasoning. So they have some known solutions in their database, and they kind of stitch together based on the prompt that you provide, but they really don't perform deductive reasoning in any kind of formal sense. So another promising direction is, especially when you have very large state and action spaces, when you kind of talk about proofs and so on, instead of using a flat RL algorithm, you can use what is called hierarchical reinforcement learning. So the idea is that you kind of divide your bigger problem into smaller problems, and you have policies that would solve each of those sub goals or sub problems, right? So it's like a standard divide and conquer strategy that allows you to solve complex reasoning problems which require reasoning over many, 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 many steps. And in fact, this is actually one of the first papers written by Tom Dietrich on hierarchical RL. And I would consider this is probably the best contribution he has made in machine learning. And there are some recent attempts at using hierarchical RL in the context of improving the reasoning capabilities of these Gen AI models. I just listed a couple of them, but there is a lot of room for a lot of work in this direction. So to summarize my talk, I kind of talked about Marvin Minsky's insight that intelligence is about shifting the test part of the generate test into the generation, right? You can think about this as almost a speed up learning problem where, as you learn more, your reasoning capabilities becomes faster per unit time. Sometimes people talk about this as system 2 thinking versus system 1 thinking. And then I gave you 3 directions. One is integration of knowledge at both training and inference, adaptive experimentation, where the verifier, you have to actually do an expensive physical experiment, and then some strategies to improve the reasoning capabilities of these Gen AI models. Thank you. Yeah, so if
Yeah,
Yeah.
for this part of the talk, we can take 1 or 2 questions
take-
and let.
Go ahead.
Oh, we'll need to have questions on the microphone for the online audience.
Yeah, I think microphone.
Hello, can you hear me? It's on?
Yeah.
Okay, again, thanks a lot for these excellent talks. You keep talking about this hypothesis generation as such. What do you mean by the hypothesis? Like trying to discover something, or what is your hypothesis? Like, for example, Alexander Fleming came up with this, he looked at, it's a classical example everyone gives, the mold thing. And then he immediately came up with this, he asked the question, what is causing that?
Yeah.
And then he created an hypothesis that this bacteria is killed by this particular fungal, whatever it is, the mold or thing is creating, is killing that.
Yeah.
So he created that hypothesis based on that. Now here, are you creating this hypothesis? Because a lot of stuff, like for example, the protein folding problem, which people talk about, those guys who got this Nobel Prize,
Right.
they didn't really discover anything in there. It's just that it discovered the structure of the protein.
Yeah.
That's the key thing out there.
Yeah.
That's their insight.
Yeah.
And that's a very important problem.
Yeah.
So that's a key insight in there, but it didn't tell why the proteins actually fold as such. So what's your hypothesis?
So I think my use of the word hypothesis is probably not in the same sense as you used. I used it in a very abstract way. You can think about this as a candidate solution for the problem that you're trying to do. For example, in the context of basically a drug design or a material design problem, my candidate hypothesis, okay, I want very high energy resilient materials, right? So my hypothesis then would be, I would be giving you some candidate materials to try, which are more likely to have that property, right? So I used the word hypothesis in that sense. Yeah, yes.
Thank you. Can I ask a question for Anuj? as
Oh
well?
yeah, sure. Anyway.
Okay. So Anuj, you said that the modern GenAI models are discriminative on the inside, generative on the outside. So I was wondering if you could elaborate on that a little bit more, because I found that very intriguing. And then my second question actually builds on the previous question is, yeah, AlphaFold did great in terms of just giving us a structure from a sequence. But when we go into the lab and try to synthesize, majority of them are not synthesizable, and often do not function the way one would hope or whatever. So I've been thinking about, is this a simple problem of saying, well, we need to optimize for properties while doing this, or is it fundamentally something that we're missing in applying AI for sort of the domain sciences?
Good, yeah. So maybe I can start about that catchphrase, generative on the discriminative on the inside, generative on the outside. The idea is that the classical models of generative models, generative AI, would focus on modeling the probability distributions using the right distribution functions, right? Where we would have knowledge of the latent variables. In a Bayesian networks, there could be hidden variables too. But the focus is on how do we get this probability distribution function. And discriminative architectures or predictive architectures are taking a completely different route, where they are making predictions, which has influenced autoregressive models. So many of these modern GenAI models, right, are using the same idea of making predictions, that instead of making predictions on target variables where you need expensive labels, what if I hold out certain part of my data and see if I can predict that, right? That's the idea of mask modeling that shows up in so many different flavors. And that has turbocharged self-supervised learning. So it's again an innovative way of using predictive architectures so that you can predict your masked regions. And if you can do that, you're essentially generating a new data set. You can mask out all the tokens and see if you can predict that. So I think that has been a conceptual idea that differentiates us or these modern methods from the historical ways of only thinking of the right distribution function. And I'll hand it over to.
Can you repeat again, Sapna, your second part?
Um, so for the second part, I was saying, like building on the previous question, right? Like AlphaFold is often quoted as the victory in terms of science for, doing AI plus science. But a lot of times the structures that it presents or predicts are not synthesizable in the lab. Like they will not, like you take that sequence, put it in the lab, and it's not going to fold into that structure. So it goes back to the fact that we haven't like really learned physics. We're just doing like sort of a pattern match, which in the past we did through homology modeling. So my question is this simply a matter of then taking that and then, tweaking it to sort of get it to optimize somewhere else? Or are we fundamentally missing something sort of in the way we are thinking and developing our models?
Yeah, I think there are multiple ways to kind of think about it. I think even in the materials design and so on, I think I have seen that synthesizability actually, you could have a very high property material, but it's not synthesizable. In those cases, what we do is that as soon as it is not synthesizable, that binary signal back to actually the surrogate model so that next time when it actually suggests a material, it would actually look for synthesizable plus the high property, right? So that's one way to do that. In this case, maybe there is not an explicit knowledge like the physics knowledge, right? This is the only way to actually kind of learn. But if you have some physics knowledge, then you can probably integrate that along with the data. And I think Anuj will talk a lot about knowledge guided machine learning, where you can actually combine both of them so that when you look at plausible solutions, right, when you care about this consistency with the known knowledge, in this case, synthesizability, that's actually satisfied. So either you have the domain knowledge to actually figure out whether it is synthesizable or not, and you provide it, right, and you integrate into the model, or when you don't have it, or if you have it partially, then you have to learn it through the binary feedback. Yeah.
Maybe I think in the interest of time, we can move on to the next part. But if there are more questions, we can take them during the break. All right. So now we are at the last part, the third part of this opening session. And we have about 20-30 minutes before the coffee break. For this part, we are going to talk about emerging opportunities in advancing the science of GenAI, inspired by needs in science and engineering. So as I think just a little slow. Okay. So as we have already discussed, right, many of the innovations in generative AI that we know today in the form of frontier foundation models have been driven by problems and needs in the tech industry, driven by applications in computer vision and language modeling. And as we have discussed already, these frontier foundation models, generative AI models, suffer from several limitations, right, that we really care about when applying these models in science. One of these limitations is their poor generalizability on distributions of data samples, on regimes where we have not collected sufficient data, right? So how do we go to auto-distribution generalization? And even if we are able to achieve good predictive accuracy, many times in science, the goal is to go beyond making predictions to understanding the causal mechanisms, to focus on interpretability and reasoning, and Jenna gave an excellent overview on that objective. We also want these models to be controllable in ways that make sense to scientists. And finally, these models have huge compute and data needs. So how can we address these limitations? And there is a lot of opportunities of taking inspiration from problems in science and engineering to address many of these limitations. In scientific and engineering applications, we are looking at multiple forms of novelties. We are looking at new types of data, new modalities of data beyond vision and text. We are looking at data that is available as graphs. For example, molecules, we have data in the form of rasters. We have data in the form of sensor networks, in the form of protein sequences, genomic sequences. We have data coming not just in the form of observations, but also in the form of simulations, also in the form of experiments that we do. There are broader classes of problems that we can look at in science beyond classification and regression. We can look at problems such as forward inverse modeling, reduced order modeling, hypothesis generation that was covered in Jana's talk too. And finally, we have the availability of a rich tradition of modeling scientific phenomena in the form of structured knowledge available as equations, laws, symmetries, knowledge graphs, mechanistic models, and so on. So given these unique features or capabilities that we see in science and engineering, what we need to explore is a two-way communication between innovations in GenAI and the needs of problems in science and engineering. Right? So that the innovations in GenAI are inspired by these needs, and these advances that we make in GenAI are used to accelerate scientific discovery. And this two-way communication is at the heart of this entire field of knowledge-guided machine learning, or KGML. And here is just a 2D view to demonstrate at a high level what is the goal of KGML, that we want to leverage not just the data that we have in scientific applications, but also the knowledge or the scientific theory available in so many different forms in how we build these models, in how we train them, in how we deploy them, in how we evaluate them. This entire area of research in KGML was summarized in a roadmap paper that we prepared in 2017 that almost laid the foundations of several directions on how we can integrate knowledge with machine learning frameworks. More recently, in a perspective article that is currently on arXiv, we have summarized where the field is currently. Research in this area is referred to by several names. So instead of the term knowledge, you may use synonyms like theory or science or physics or process. Instead of guided, you could use synonyms like informed, aware, infused, enabled, based. Right? And ML could be replaced with AI, NN, data science, and so on. Right? So you can mix and match these synonyms from these three categories, and you would come up with terms like physics-informed machine learning, physics-informed neural networks. They have subtle differences, but at a high level, they're exploring the same goal of how do we bring knowledge and data together. And this is a very rich area of research. There are almost more than 100 papers published every year now in this field, and these advances have the potential to address many of the limitations that we discussed in the last slide that apply to black box GenAI formulations. These KGML principles have the ability to improve out of distribution generalizability. They have the potential to improve the parameter and label efficiency. So how can we build models using smaller compute, using smaller number of label data? How can we move beyond predictive accuracy to interpretability and generating novel scientific hypotheses? So these are just some of the driving goals for research in the field of KGML. And if we look at the timeline of activities that have inspired the development of KGML, historically, there are different schools of thought where that have explored the idea of using knowledge and data together. For example, Bayesian formulations provide natural way to encode knowledge in the form of priors. Right? And we also have methods from constraint optimization, from symbolic AI methods. Right? In the more recent times, one of the projects that really spearheaded directions on incorporating knowledge with machine learning was the NSF Expeditions project on climate change, led by Vipin Kumar. During this process of working on climate change problems, we realized the importance of incorporating the knowledge that is encapsulated in the form of these climate models, along with data-driven approaches. So we had one thought article in 2014. Similarly, there was another article in 2016 with very similar terminologies, theory-guided machine learning, but for material science. Right? So you could see that these ideas were emerging, but in isolated communities, in climate science, in material science. In many ways, 2017 could be thought of as a watershed moment for the field of KGML, with several developments that happened. One was this perspective paper on theory-guided data science, which was an initial terminology for KGML that tried to connect all these different advances happening in climate science, in material science, in hydrology, and provided a vision for what are the future possibilities. Parallelly, in 2017, we had the development of the seminal work on physics-informed neural networks, right, that are using machine learning neural network models to solve partial differential equations that are almost ubiquitous in many physical sciences applications, with supervision purely from the knowledge of the PDE. These developments have inspired several streams of research in KGML for different applications. We have a long-standing research direction in KGML for aquatic sciences. We have KGML for biodiversity science, for organismal biology. We have KGML for epidemiology, for agriculture. Many of these activities have been supported and enabled by funding from federal agencies such as NSF. And then we also have a lot of activities since 2017 in EI4X for different communities, EI for chemistry, with the development of equivariant neural networks, EI for protein folding and the flagship model of AlphaFold, EI for climate and weather, and there are many more recent models that are developing now. At different points of time, there have been perspective articles, review articles, survey articles, summarizing the state of research in this area of KGML. And as I mentioned, many of these developments were possible because of calls from funding agencies. So going back to the Physics of AI program of DARPA, to the series of workshops held at NSF on AI-enabled scientific revolution that informed many of the recommendations in the ACED program, Accelerating Computing and Enabled Discovery. And throughout this process, there have been several community building activities that have happened in the field. Several symposiums, tutorials, workshops on KGML and AI4Science in general, which is a broader field. Many of these organized by our team, but more widely by the community. Most recently, a bridge program that we organized at AAAI, and it's a series of bridge programs that we have been organizing. And just last week, I was at University of Michigan, where the Schmidt Sciences Foundation had an entire workshop on KGML organized by their postdocs. So this shows you the excitement that is there in the community in the field of KGML. And given the diversity of disciplines, researchers that are exploring problems in KGML, it's important to provide a structure, an organization to the different KGML advances. In our perspective article, we've tried to provide this structure in the form of a multi-dimensional, 5-dimensional perspective. Each of these dimensions capture different aspects of the nature of the problem that we are dealing with in KGML. So these dimensions can be thought of as different questions that a scientist can ask to situate their research in the rich KGML landscape. A longer discussion of this 5-dimensional figure is available in the form of a tutorial. The link is provided over there, which is a recording of the workshop that happened last year at Minnesota. But just to summarize some of these dimensions, the first 2 dimensions capture the variations in how we formalize knowledge, right? What is the exact format? Is it in the form of PDs? Is it in the form of knowledge graphs? Is it in the form of our knowledge of a mechanistic model, which in many ways has a modular structure? Or whether we are dealing with perfect knowledge or complete knowledge, ranging to imperfect, approximate, and missing or partial knowledge. There are dimensions that capture how we integrate knowledge in ML frameworks, ranging from process-centric to ML-centric. And finally, we have different use cases that are motivating research in KGML, ranging from forward modeling, inverse modeling, reduced order modeling, equation discovery, downscaling, subgrid parameterization, and so on and so forth. So these settings on these dimensions are still not exhaustive, right? There are many other settings. And we can dwell into any of these dimensions in much more detail. But in the interest of time for this talk, let me talk about only one of these dimensions and the advances that are happening on the different settings of this dimension that are relevant to GenAI. So when we think of the different ways we can incorporate knowledge in ML, right, there are broadly 4 different approaches that we can explore. The first approach is to change the learning objective or the loss function in deep learning. Seminal works like physics-informed neural networks explore this for solving partial differential equations. But when the knowledge is approximate, right, when we don't have perfect, or when we cannot assume that the knowledge is perfect in the form of a PD, but we still have some partial relationships, we can explore formulations like physics-guided neural networks or PGNNs. Another approach for incorporating knowledge is by changing the architecture. So there is a lot of research on incorporating invariances, symmetries in neural network architectures, for example, equivariant net. And in many ways, convolution neural networks are a great example that already encode some form of knowledge, which is the translation invariance. But in sciences, we can go beyond translation invariance to look at other forms of knowledge that we can incorporate. There is a lot of recent research that has happened on how we incorporate knowledge in the learning of feature representations so that they're structured by knowledge, where different subsections or segments of the feature space capture information in a domain structured way. And finally, we have an entire field of post-training models that once we have built a generative AI model or a foundation model, how can we steer its generated outputs that align with knowledge, with techniques like in-context learning, plug-and-play guidance that Aryan described, and even opportunities for using reinforcement learning, as Jana explained, in this particular direction. So advances that are happening in these 4 different buckets are providing novel ways to think of the deep learning advances that have enabled GenAI. We can think of novel ways of doing representation learning, novel ways to think of interpretable AI, novel ways to steer the generation of outputs from GenAI models, novel ways to build foundation models and agentic AI systems. Let me go a little bit in more detail in some of these dimensions. So, for example, when it comes to representation learning, right, there's a lot of research that is happening in biodiversity science in the NSF-funded Image Geomics project, where we are structuring the feature spaces that we are learning from images of organisms like butterflies, birds, fishes, that capture our information of the process of evolution, that different segments of the feature space capture information at different levels of ancestry in the phylogeny. This is providing directions of aligning the features, these abstract representations that we learn in deep learning, with interpretable, explainable concepts. Right? And these ideas can go beyond biodiversity applications to mainstream vision and language problems. Just like we have self-supervised learning frameworks where we explore mask modeling strategies, exploiting some form of structure in the data, can we explore other forms of structure in the data to create counterparts for mask modeling in science? Can we do this masking in a more principled way that makes sense to a scientist? Can we pre-train our representations using simulations that we have available in many applications with varying degrees of fidelity? Can we use knowledge-guided loss functions as a pre-training task for self-supervised learning? Can we change the neural architectures? For example, using being inspired by the modular structure that we have of mechanistic models? Or can we rethink how we develop attentions, right? Where we do not only let the data drive the learning of the interactions or the attentions, but we also leverage some form of knowledge of how different tokens should interact with each other. And Aryan has also already gone through the guided inference portions like plug and play guidance and in context learning that we can rethink in the presence of domain knowledge. In the world of foundation models, where we have a pre-trained and fine-tuned approach, right? These advances in KGML sit at different portions, right? They can help us rethink pre-training, the architecture of these models, the fine-tuning during post-training. So this is a very rich space, and I'm happy to discuss this in more detail, but in the interest of time, I'll hand it over to Aryan to discuss the use cases.
Thanks, Anuj. Yeah. So now I'm going to talk about, I'll try to go over it quickly. I'm going to talk about some applications and use cases where we are already seeing some break-ins. People are already thinking about these problems and also outstanding challenges. And of course, a lot of it is in the report, which I recommend everybody to read. So one of them is there is a lot of interest in building digital twins and emulators. So there are lots of natural and human-made processes which occur over large spatiotemporal scales, and there is a growing interest in developing emulators for those processes in scientific and environmental systems, and hopefully also incorporate human feedback somehow. A popular one, which I've learned from my colleagues here, is how a lot of molecules, proteins, and stuff is not only about structure, but also dynamics. So molecular dynamics, simulators for molecular dynamics is a big interest. There are lots of other domains, right? Weather sciences, we are trying to simulate climate, or in transportation, simulating traffic in urban centers. It's a very hard and important challenge. So these are lots of interesting applications. Already people are starting thinking about for these methods. But of course, a big challenge of building these digital twins and emulators is we really want to use them for rare events, to predict rare events, to estimate rare events. And that's what we have limited data about. So perhaps thinking from the knowledge perspective and other perspective is going to be important here. Another application, my favorite one, is experimental design, where we are thinking about searching over a space of, let's say, objects. This could be drugs, hardware chips, materials, and we want to achieve a design goal. Typically, the design goal is I want to find the best material, but this could be other design goals, like I want to find the most diverse ones and other things. A big challenge of these domains has always been that all of these objects are typically high dimensional. They're typically discrete in nature. So directly searching over this space has always been challenging. So with these generative AI methods, there is this new opportunity to convert this hard search problem into this sampling problem. And hopefully we can sample good candidates for our experimental design. An example I gave in the variational autoencoder, for example, you get this low dimensional continuous embedding, and you can search in that space, and you can decode it back to get your original structures in the original space, and then you can evaluate them. But a lot of us who work on these problems know that experimental design is not only about exploration, and there are lots of challenges. A big one is we want to do that, and this was alluded earlier in the RL part also. We want to do this exploration in a resource efficient manner. I don't want to do thousands of millions of experiments, which are really expensive. And we care about all gazillions of properties, right? We care about lots of constraints. We want to handle multiple fidelities of evaluation. Evaluation is not a particular experiment, but it could be some simulation. You could do a faster simulation. You could use computational models. You could do literally a wet lab experiment of different degrees. So how can we handle that? How can we handle diversity in candidate design? So these are very, very important challenges which GenAI alone cannot address. A promising direction for this, which was mentioned earlier as well, is adaptive experimental design, where we carefully think about actively acquiring samples or actively doing experiments. And I am happy to talk about this later, but here is one paper if somebody wants to look at it. And of course, a big deal about, especially with language-based generative AI models, is now we have these natural language interfaces to lots of applications, and we are starting to think about using them in research workflows. So an example is semantic search engines. So can I just, when I generate a molecule, can I search in the literature if parts of these molecules are toxic or not? This is where a lot of work in RAG or retrieval augmented generation comes in. We are also starting to think about using these language models as orchestrators for code or APIs. So for example, an orchestrator for an experimental lab API. Of course, program synthesis and auto-formalization is important for lots of other, like proving these systems, and hopefully by generating that, that will be useful there. And there are some examples of these services which I've listed, but there are lots of others as well. And there are lots of challenges here. Hallucinations is a big one when we work with these systems. It's still persisting. Trustworthiness, right? We want, especially in sciences, we care about sound inference, not just plausible inference. And I do believe a big part of it's going to be really thinking about human-centered design as well, because a lot of it, when we are trying to work with these systems, defining clear human intent is not that easy. So especially thinking about systems when they are going to generate, let's say, a lot more, let's say, large amount of content or, let's say, text. And a human cannot possibly, we are reaching stages where a single human, it will take a lot of effort for a human to evaluate those things. So how do we think about human-centered design in those settings? So these are the 3 use cases, but of course there are lots, and we'll hear about all of them in the workshop in 2 days, but there is a lot more in the report that you can go and read, and yeah, we can take some questions. Yeah.
Thank you. And I think we have been running late because we started late about 20 minutes. We caught up 5 minutes of that. So I would suggest we take 5 minutes break, and then we start on the panel, and then we'll delay lunch only by 5 minutes. So the next panel can be hour and 15 minutes as well. All right, thank you. Let's take a break and we get started for the panel. Please take your seats.
Good afternoon. I'm going to first quickly introduce our panelists. My name is Raj Acharya. I'm the moderator. I'm at the National Science Foundation, IIS. I'm a program director, and I'm a faculty at Indiana University. So,
Hi, I'm Nikunj Oza with NASA. I lead the data sciences group there. We do, pardon me, we do machine learning R&D for the full range of NASA problems. So this includes aeronautics, earth science, space science, and human space exploration. I also have been leading a project involving machine learning for aviation safety and also adding other components to that, like human performance and fatigue, and also identification of human contributions to safety. Thank you.
Is this on? Can you hear me okay? All right, great, thank you. So good morning, everyone. My name is Jarvis Haupt. I'm the faculty here at the University of Minnesota in the Department of Electrical and Computer Engineering. I'm also, I guess, I have a couple administrative kind of sections too. I'm associate department head, and I'm also the chair of the editorial section of electrical engineering and systems science at Archive. So among other things. So my research interests are broadly in signal processing. That's sort of been my path since I was in graduate school. And back then, signal processing meant kind of something, I think, a little bit more focused. But in recent years, like everything else, it's broadened quite a bit. So, you know, I dabble in things like optimization and machine learning and data science. I created a machine learning data science course for our department a few years ago. So, you know, my interests in AI are also kind of multifaceted. So recently we wrote a paper for the IEEE Signal Processing magazine on using AI for signal processing education. So I'll kind of draw on some of the insights that we uncovered in that effort here. So I'm excited to do this. Thank you.
Good morning, everyone. My name is Lior Koresh. I'm a senior manager at IBM Research, leading the mathematics and theoretical computer science group. Part of our mission is to advance computation in general, but in particular in the domain of AI. We have doubled our efforts on trying to bring statistical AI and formal methods together, specifically for scientific discovery. So hopefully that background will be relevant to this conversation.
as a background, today in this panel, we'll be discussing algorithms and methodologies for creating AI testbeds for real-life situations. At NSF, we had an AI institute call last year. It's called Strengthening AI. And the whole idea was we just gave the specs. And the specs was grounding. That's the fundamental principles on which the AI algorithms was based on. The second one was alignment. Alignment basically meant, does it align, the output align with what we expect as humans? And the third one was instructability. Instructability is, can the algorithms and methodologies learn from humans and other AI systems? So what we're going to do is sort of have that in the back of the mind. And we have about 7 questions I will ask the panelists. I've chosen which one answers the particular question. After we finish the 7 questions, we will open it for the audience to ask questions. So the first question will be for Jarvis. And the question is, how can we ensure that GenAI models for science not only generate realistic outputs, but also respect physical laws, support logical reasoning, and provide scientifically grounded explanations? Can these models be formally verified And how do we distinguish between hallucination and genuine novelty?
All right. So thank you. So in full disclosure, we had these questions a bit ahead of time too. So I've had a little bit of a chance to digest some of these. So I'll take them in parts, and I'm going to refer to Raj's screen here just to remind myself the different parts. So the first one about generating realistic outputs and respecting physical laws. I think one of the things that so every year I teach this machine learning course, and I kind of anecdotally poll the students and say, how many people use AI and what do you use it for? And over the last couple of years, of course, this has grown exponentially. And their sort of interests are not exactly what I would expect. A lot of them say they'll use it to do things like, I could say something like transcoding. They'll take a section of text from the textbook and say, explain this to me in a Gen Z way or something like that, as somebody told me once. So the use cases are sort of diverse, but one of the things that I always try to impress on the students too at that point in that conversation is that AI shouldn't be seen as an oracle, right? So bringing that back to the context of this question, how do we make sure that we respect physical laws and have scientifically grounded explanations? So the first one is not to overestimate the tool. These things are amazingly powerful tools, but if you ask it to take a large composite number and factor it into two primes, right, the essence of like RSA decryption, you can't sort of do it, right? I mean, it's not like it's going to look back in a pattern of human knowledge and say, oh, here's a connection that's going to let me do this. These are kind of known to be hard problems. So I think that has to dovetail with the validation schemes that we use, right? There has to be physical validation on some of these things. I mentioned this article that we wrote, and a couple of the things, the challenges that we were looking at with that were the same as in scientific endeavors that arise also in the educational space. So you say, how do I make sure that I'm giving proper, correct educational content to somebody, generating it with an AI tool? And the couple of things that come to mind are, one, you have foundational credibility. This comes back to kind of appealing to physical laws and saying, if I have a principle, I have a fundamental equation, and I can verify that, and I can demonstrate that it's being verified. And one of the ways that we kind of advocated doing that in the paper was creating something like JavaScript applets that you can do in kind of a no-code approach using AI to demonstrate these principles. And the other one is vicarious credibility. So in an educational space as well as a scientific space, it's important to see that what you're getting are kind of data from reputable sources. You know, you can query the AI and say, only give me kind of insights from highly cited resources or something like this. And you can kind of quantify some of these efforts. So I think some of those same ideas translate to using these in scientific applications, that we can appeal to these notions of foundational and vicarious credibility. And it might just come down to also kind of doing the hard work of verifying these things ourselves, maybe in an automated fashion. But the last thing I wanted to mention here, because I want to save time for everyone to answer their questions, is the question here about how do we distinguish between hallucinations and genuine novelty. To me, I think this is a fundamental question in science in general. And the way that we've done this throughout history in kind of our disciplines is a peer review process, right? There's this notion of humans need to somehow be in the loop to double check things. You know, even if you have a theorem that's proven, you'll put it up in archive and people will look at it and say, oh, there's a loophole here, or you missed something there, or whatever. So there's a constant validation process going on in science. And to me, I don't see necessarily that when we automate sections of this, that whole process, that pipeline breaks. I think it might change, it might look a little bit different, but I still think humans in the loop is a kind of a critical part of the validation scheme overall.
If not, go ahead.
No, so I just want to add that indeed, one of the things that we see is that Gen AI is not a end-to-end solution necessarily, right? We have to think about it as a tool that has some great virtues, but also fundamental limitations. At least at the current capabilities of Gen AI, it is a good idea to think about complementarity of Gen AI with other maybe formal tools or other machinery in order to make sure that hallucinations and other implications of not necessarily following or adhering to all physical constraints are indeed satisfied.
I think in signal processing, there is a famous saying that you cannot beat the sampling theorem. And the only way you can beat the sampling theorem is with a priori knowledge. Hallucination is created because some sort of sampling is violated, right? So from an information theoretic point of view, this is sort of an approach one could take on why hallucinations are generated and how do you mitigate them. So I'll move to the second question. What new principles and frameworks are needed to evaluate GenAI models in science, especially with respect to uncertainty quantification, out-of-distribution generalization, reproducibility, and hypothesis validation?
Thank you. So yeah, this in some way also relates to the first question, but while we want to respect physical laws and the like, we don't want to have too much respect. And I mean, I guess, yeah, so I mean, as you know, Box, the greatest modeler, as he said, you know, all models are wrong, but some are useful. And it's more fine-grained than that, right? Different models are useful to different extents in different operating regimes. And in some cases, we just don't have any idea. So we don't have any kind of model or human knowledge or the like. So ultimately, it's going to boil down to some kind of like a mixture of experts. Sorry, I did my PhD in ensemble learning, so I tend to think about ensembles and committees and the like. So ultimately, it boils down to kind of like almost what we do, right? We know different people's expertise. And so in this case, we know we can figure out different models' expertise, whether it's data-driven models or physics-based models, and use them in ways that are appropriate. Thanks.
Thank you. Any questions, comments from the panel? Okay, Lior, I will have the next question for you. Which Gen AI approaches, such as diffusion models, autoregressive models, VAEs, normalizing flows, or GANs, are best suited for different scientific problems? What criteria should be guide for these choices?
Okay, so first of all, maybe let's start with the criteria, because obviously there are different tasks and each task has different emphasis on different properties. So one question is what type of data we are dealing with. What is the volume of the data? What is the quality of the data? For instance, GANs require a lot of high quality data sets, while VAE can actually work with relatively small data. What is the dimensionality of the data? Are we talking about voluminous, large dimensional data that typically can be handled with diffusion models or poorly with normalizing flows? What is the structure of the data is even more relevant, right? So if we have sequential data, obviously autoregressive type of approaches would make more sense. If we have tabular data, we often resort to VAEs. If we have continuous space type of data, diffusion models, normalizing flows are typically more appropriate. Now, the next question is what type of scientific requirements we have, right? How important it is for us to incorporate some physical constraints or laws, and normalizing flows seems to be one of the better approaches in terms of being able to encode those exact conservation laws. Diffusion models can do that also, but more in the form of guidance. And we can also do things of that nature with VAEs. We can work in the latent space and incorporate some of our knowledge in one way or another. Uncertainty quantification is another big question. So if we are really careful as for exact representation of uncertainty, we may want models such as normalizing flows that allow us to exactly estimate the likelihood and the posteriors. VAEs can also enable us to do that with a lower bound and approximations, but obviously there are different propositions in that regard. Interpretability is another big question in terms of scientific criteria, how much we care about whether we understand the intrinsic relationship or we are happy with a black box that can provide us good input-output relations, VAE is one of the better options in terms of interpretability. And I guess it was also mentioned in the previous talk, controllability is another important virtue. Then, of course, there are also questions related to computation, right? So if we care about generation speed, we may choose approaches that are more scalable computationally. We may want to care about training stability. GANs, for instance, is not the best approach for training. Do we care about memory requirements and so forth? Now, when it comes to the question as for what type of applications each one of those models are excelling at, so if we think about diffusion models, they are really doing very well when we deal with high-dimensional data sets that have complex multimodal distributions, and that seems to fit rather well molecular conformation sampling, protein structure generation, and any other problem where we have some sort of continuous underlying physical law that is governing the behavior, and we are happy to search in that sort of vicinity. Autoregressive models, as we mentioned, are very useful when we look into sequential data. So whenever we have causal elements, whenever we have time series or a reaction pathway predictions, problems of that sort would be very natural choices for autoregressive models. When it comes to VAEs, they are rather interpretable when it comes to the latent space. So problems like chemical space exploration, dimensionality reduction, when we have a high throughput of experimentation, they seem to be very appropriate for these classes of problems. Then, sorry for the long list, but I try to hopefully address all of them. When we talk about normalizing flows, they have a wonderful ability to represent conservation laws, and that may be a good fit for problems where such conservation laws apply, right? So problems that involve thermodynamical relations or other conservation laws such as the phase space sampling and so forth. Lastly, per GANs, I'm not a big fan of GANs, so I hope that I'm not trashing them unnecessarily. But when we do have abundant data, we have a lot of data, we would like to explore a large space, we would like to generate a lot of synthetic experimental data, they seem to be the right choice. But to summarize all of that, there's no one method that fits them all. We have to be conscious as for what the requirements we have, and with that make the appropriate choices for the right method for the right purpose.
I was just going to say, I don't think I have anything to add. That was a very comprehensive overview, and I appreciate it. Thank you.
I have to admit, I heard the question beforehand, so I didn't come completely. I'm not that talented.
I would like to add that neurosymbolic and multi-representational learning is a very important kind of methodology. So you have information in some sort of a metric space, and that is typically machine learning, and which you compute a norm. And then you have information in the logical space where you have rules and you have logical elements, and there is some sort of an embedding where you transform or you embed the logical space and the metric space into some ways that can relate to each other. And as talked today morning, there's a bunch of hypotheses, and in order to, you don't need to satisfy all the SAT. You can use what's called as a partial SAT. And then this is a very good way of combining logical information, rules, and other graph theoretical knowledge with the machine learning kinds of knowledge. So I will move to the next question. This is for Jarvis. What is needed to build meaningful GenAI testbeds for science that include representative datasets, robust benchmarks, and full stack integration across platforms and workflows. Before Jarvis can answer, I'd like to say that last week, NSF announced a planning grants for the AI testbeds. They announced, I think, 2 planning grants. The idea here is that after this is fully implemented, in a realistic situation, to have testbeds where the algorithms and methodologies can be verified. So the first 2 planning grants have gone out, and that's the status of it. So Jarvis.
So thank you. So I think this sort of inspires me to think along a couple different axes, this question. So the first part is, when you think about test beds, I think this came up in a talk earlier this morning, and Lior mentioned this as well. There's this notion of that effective kind of testing or problem solving in general involves decomposition, right? Maybe we're all kind of victims of our own expertise in a lot of ways, that when we think of a problem, we often in our own minds synthesize it from the bottom up, and we sort of understand the full scope of knowledge, and we dive in as subject experts in our own areas. To me, and from my maybe anecdotal experience, I don't think AI is necessarily that. It is in some things, right? You can ask fairly detailed questions and get fairly detailed answers, for instance, with an LLM. But I think the most effective strategies that I've seen are the ones that decompose these tasks into smaller substeps. And I think this dovetails, like I said, that was mentioned in the talks this morning, with this notion of like unit testing that you might do in a software development scope, right? So you have your overall program or app or whatever you're writing, and you'd say, rather than sort of test end to end, you kind of write little tests for each piece. And I think something like that is probably also germane here. I mean, that would be my recommendation, I guess, would be that we have to think about this as an assistive technology that can help at intermediate steps. And maybe the onus at this point in time, maybe not in 5 years, but at this point in time, the onus on us might be to decompose it into those steps and look at the testbed kind of validation step as the sub-steps, kind of thinking about this incrementally. The other thing is that, as I kind of dwelled on the AI timeline, if you will, it was a nice overview this morning. I was sort of thinking, like, you can also characterize this into epochs or epochs, depending what your terminology preference is. So in some sense, like, we had several thousand years of human development where people created content, and a lot of it was analog and a lot of it was digital. And suddenly we had this big corpus of documents. And then we set out these language models and trained them on everything that was kind of existing in time up to that point. And that was maybe a first time step. And as was mentioned earlier today, they kind of stagnated until we put humans in the loop and said, okay, here's what we found, but is it any good? And then you could think of that as sort of one generation. It's sort of human generated content, computerized distillation of knowledge. Then you had another human interaction, and then maybe another computerized interaction. So I don't know how many epochs in we are at this point, but I would say we're, order less than 10, right? There's been a couple of these things. And I sort of see in my philosophy is that for these things to really kind of advance, to sort of validate these, I also see humans playing a crucial role, at least at the outset. Like I said, there's this tendency to think AI is going to automate everything for me. But I think I think we'll achieve kind of much more and at a much more rapid pace if we remember that this isn't just a burden to sort of inject ourselves into the loop. This is actually what gets to the next level, as it did with the first kind of reinforcement learning trained paradigms that we heard about earlier today. So again, my suggestion would be validation kind of at the unit level. I mean, I think we'll get to the system level, but I think to be kind of robust and precise, you want to kind of take problems, validate them in smaller times, in smaller chunks, and then also think about mechanisms where you can put the human into the validation process. I think that actually would end up benefiting more than the time invested, much as, the thousands of years of human knowledge being distilled into the first kind of GPT models, if you will. There's a lot of knowledge there, but it needs a next step, and it needs the next step and the next infusion of maybe innovation that I don't think the models can provide autonomously just yet.
Yeah, so in a lot of the discussion, I think here and in general, we assume in machine learning problems that there's a large data set we're going to train a model on it, do some testing. If it works better than everybody else, we brag about it, write the paper, and we're done. In many problems, it's not a one-shot process of constructing these data. For example, it's like NASA has airborne science campaigns, earth science campaigns, where they plan flights of, let's say, UAVs or even, say, a single large aircraft over many days. So they'll collect some data, takes a little bit of time, maybe a day or two, to assess those data relative to the earth science models that they have. These are physics-based models, in some cases data-driven, and based on that, plan what next data collection they should do in the form of flights that they should conduct. So for test beds and benchmarks, ideally, and physical test beds, but otherwise virtual test beds or virtual labs where we can assess models for their ability to inform us on what additional data need to be collected, what gaps we still have in our knowledge, would, I think, be something worthwhile for appropriate communities to work on.
Thank you. So the next question is for Nikunj. How can GenAI support learning across different scientific domains with varying data availability, such as from well-instrumented fields like astrophysics to data-sparse ones like ecology or hydrology?
So seeing this question reminded me of NASA's vision for digital twins, and in particular Earth system digital twins. In addition to the roles I mentioned before, I do have a program management role on information technology for Earth science within NASA. And so as part of that, we developed this vision where the thought is that within Earth science itself, there are different domains that have mostly been stovepiped, which should not necessarily be. For example, atmospheric science and ocean science have mostly been stovepiped, but there is this, what is called a planetary boundary layer, where there is stuff going on where the atmosphere impacts the ocean and the other way around. So there's the thought that maybe if we have digital twins developed first by atmospheric science and also some by ocean science, then maybe we can plan to match them together and use those to help inform us across the two domains. That's just one example. There are probably other examples in other. I'm most interested in doing this within domains rather than across domains. Thanks.
I think, like in today's talk earlier, it's a fascinating talk, very nicely done. The issue comes down to representations, some sort of a mathematical representation for any particular domain one is talking about, and what all we learn from it. And then when we want to do the other domains, which doesn't have the enrichment of data availability, maybe one can go into a latent space and then use the models which was done there and transfer what all knowledge one has accumulated. Maybe this is one approach one can take. Any other?
Yeah, so I would like maybe to add on representation. So it is probably really fundamental because we are trying to bring two somewhat non-consistent words of representations together, right? We typically have numerical data that can interact with itself in some manner, and we have symbolic knowledge that we want to somehow force to talk with each other. And you mentioned neurosymbolic methods before and now representations. If we find a way to embed both of them in a common space where the two can exchange value, can exchange their level of confidence about either the data or the knowledge, because neither of them necessarily is correct, right? We admit that that was mentioned before. The knowledge can be wrong. We know that the Newton laws of mechanics are not correct. We have relativity, and we now know that that probably is incorrect as well. It is not consistent with quantum mechanics. So that's also incorrect, probably, right? So So the knowledge is not necessarily correct. The data is noisy and sparse and all of those things that we typically trash data to be. We need to be creative in finding some common space where the two can really interact and provide additional value in a complementary way. And it can be in a sequential manner, as we saw before in one of the talks about having a loop with verification or validation that is a separate step after generation. Maybe there is even a better opportunity if we try to find a common space where they can exchange the value in the generation itself, right? So to generate and validate in the same one step.
Any other comments? So the next one is for Jarvis. What are the best practices for building effective collaborations between AI researchers and domain scientists? How should we train the next generation of scientists to work alongside Gen AI tools?
So I think maybe I'll answer these kind of in reverse order. So the first one about training the next generation, I think to me, the main thing is just to kind of impress a couple core ideas. One is, again, this idea that these agents as of now are not oracles. So understanding what they are. Second is, again, this idea that I think all of us do, but maybe it's not as crystallized in our minds as it is when we kind of look at these kind of applications and the need for it, is this idea of taking big problems and decomposing it into sub-problems, not necessarily seeking the end-to-end solution. I mean, we all do this when we collaborate with people. We all know that there's different sub-problems that people are, qualified for or working on at this moment or whatever it is. So it happens all the time. But I think if you're training people that don't have that, partial lifetime of experience in this area, is to say, like, these are the methods that you want to look at. Divide and conquer, decompose and address, whatever you want to call it. These kind of methodologies that are fundamental to a lot of scientific disciplines, I think, are also going to be fundamental when using AI. And again, anecdotally from my own use cases, they just tend to work better when you can take your problem and decompose it into pieces and try to ask for assistance solving each piece. The other one that if I get up on a soapbox occasionally talking about AI, is that I think one of the things to keep in mind is that, I'll give an analogy. So, for a lot of us, right, a lot of our work requires calculations, but we don't do multiplication and stuff longhand anymore very often, right? So there's technology that can be a means to an end for productivity increases. And if I think about the next generation of scientists, right, so people that are younger right now are kind of coming up in an age when a lot of these things can be automated. You could say, write me a program to do X or whatever it is. And I think that incentive is a little bit mismatched, right? So for me, I kind of grew up in a mostly analog era, I guess. So for me, I could see that as being a benefit because I could do it myself the other way, but maybe it's more expedient for me to ask for assistance. I think the real challenge, and maybe a danger, if you will, is for the next generation to think about this as just a drop-in replacement for knowing those fundamental things, right? So we want to impress upon people that these should be technologies that are used to incentivize productivity, not to incentivize maybe laziness, for lack of a better word, right? That's a key thing, I think, that needs to be impressed, because for a lot of us, it came naturally by our upbringing. For the younger generation, I think this might have to be a kind of an artificial thing that that we teach. Best practices, I'll just maybe make a comment or two on this quick. Again, this idea, and I think Nikunj mentioned this earlier, that there are distinct expertises, in any discipline, right? So this mixture of experts idea, I think, is pretty pervasive, right? I think GPT-4, it's rumored to be using something like this, right? They train a bunch of individual models and use a mixture of expert type kind of aggregation. So I think that this notion of, we all sort of want a one-size-fits-all solution, but I think if you're thinking about how scientific, domain experts work alongside AI researchers, I think the goal should be, in my opinion, maybe thinking about building specialized techniques or specialized models perhaps for different disciplines. And then if you want the one-size-fits-all, there's ways of aggregating these after the fact. I think OpenAI is probably taking a similar tack, but that seems to be something that's far more scalable than asking for this end-to-end kind of solution.
comments?
As far as the first part of this question was about building effective collaborations between AI researchers and domain scientists. There's a model that I really like called the Frontier Development Labs. It's mainly run by an organization called the Search for Extraterrestrial Intelligence, or SETI, or SETI, but NASA has had significant involvement in this. It's an 8-week program in the summer, full-time, where they have 2 PhD students or postdocs in AI and 2 in a domain science, and they work together full-time plus for 8 weeks and come out with some paper or presentation. Oftentimes they have published their work as well. This is just nice because they're full-time, fully engaged in this. Since they're PhD students and postdocs, they don't need a lot of sleep. Just give them pizza and they do great work. And I have found that a lot of what's produced, actually, there's a lot of future work also left in there. And those can be good, that can represent good material for grant proposals. And that's also a good way that, the people, they really learn about not only specific considerations of the other domain, but generally, let's say, a different way of thinking. And that's a good thing for people early in their career to gain.
Actually, I did my PhD here at University of Minnesota, but I did all my research at Mayo Clinic. And this was a very good model. The model is the student is the integrator of knowledge between the 2 different advisors. And I would teach, the domain scientist, the AI and the computer science part of it, and vice versa. So I think I like this model very much. Okay, I will go to the last question for Lior. And what are the most promising short-term applications and long-term challenges where GenAI can accelerate discovery? Can GenAI meaningfully assist in scientific creativity, literature synthesis, or hypothesis generation, even when mechanistic understanding is limited?
So I would even start before we get into literature review with the first step that we hopefully do when we start engaging in a scientific problem. We ask a question, right? So how do we form a question? There was a very nice work of DeepMind in guided intuition. What they did was effectively they brought from node theory. There are different nodes with different algebraic characteristics, different geometric characteristics. They just put a neural network between them and try to predict one from the other. And even though they did not get an explicit relation that explained why one algebraic characteristic of a node is similar to a geometric one, they did find some implicit relations that sort of give you the intuition, oh, this is an interesting question to explore, right? So we can see that already with asking the right questions, we can use GenAI to ask such questions. We can use GenAI also to provide us some guidances for what are the edge cases of each theory, where things do not work very well and maybe we should explore further. The next step is, of course, the study, right? And in the study, obviously, GenAI can be very, very effective at aggregating, even curating and providing some sort of scaling as for what type of prior data and knowledge we would like to incorporate as some prior knowledge that we bring into the discovery process. Travis was mentioning the composition, right? So we see some relatively new and exciting ideas as for how GenAI can even do some form of decomposition, a chain of thoughts, a graph of trees, a chain of graphs, a graph of trees, and so forth. There are different ways that we can take a problem and decompose it hierarchically or as a graph. And now AI can do some of that. And potentially that can help us even when we try to challenge a very complicated problem. How do we even start? It's very difficult to charge all the aspects of the problem in one go. If we can decompose it into some smaller loosely coupled components and address each of them independently, maybe this is something that is more manageable. We can also distribute such a problem with other agents. It could be human or they can be AI agents, but this is enable us to scale also in terms of the number of entities that tackle such a problem. One topic that I guess we all have already saw is that obviously GenAI can be very useful in hypothesis generation. It can be very creative. Sometimes we trash the hallucinations of GenAI as a negative component. It can, if we embrace hallucinations, that can also help us, right? We may want to be as creative as conceptualizing that the time is relative, space is relative, but speed of light is constant. You need to be hallucinating a little bit to come with such proposition and come up with relativity, right? So hallucination is not something that we should regard necessarily as a negative component, as long as it is coupled with a formal method that can verify that we throw a lot of darts now. We then come and see which one of them actually fit into our target, rather than just keep on throwing them, right? So hypothesis generation can be one of the near term, or already one of the near term usages of GenAI. Of course, it can be useful in experimental design and in the art of hypothesis testing. We may want to think about using GenAI for augmentation of rare events. So oftentimes we would like to explore specific scenarios in our distributions that are a little bit at the edges, and GenAI can help us to generate such data sets, and then we can explore them. And of course, we can do analogical reasoning. So we may be able to bring some concepts or rules or ideas from one topic to another by asking about analogies, and typically we can get at least interesting results. The last one on the short term is something that we all do. They can be very, very helpful when we write a report, right? We can use GenAI to write our papers or to write the report to the NSF or other agencies. I guess I'm not telling anybody a secret here. The long-term challenges are a little bit more tricky, right? So part of the challenge is how do we deal with multi-scale type of problems, or multi-physics, multi-scale. And here you may need to incorporate simulation and physics of different forms in one coherent, in multi-scale, right? In one coherent framework, and that is challenging. Causality is also something that for now, I believe, is a little bit more challenging, especially with complex systems. We would like to be able to bring the theory and the data into one unified space where they can talk with each other, and that's currently a little bit outside the realm of what GenAI can do. And the last thing, maybe again related to theories, is it may be at some point we now have, in addition to large language models, we have large reasoning models. Maybe they'll be able to generate some propositional theories, or at least serve as a first gatekeeper for some of the hypotheses we have. And then those that pass that secondary, let's say, or the primary filter, those that pass that, we can actually delegate further into formal methods that are computationally very expensive, right? So we can think about it as a two-tier filter, right? The first filter would be large reasoning model. Whatever past that, we will take into a formal method that will do a more rigor type of analysis.
Yeah, well, one other advantage is what if out-of-the-box thinking. These are very easily done by these sorts of methods, and those are invaluable, right? I mean, these are how we can expand the creative dimensions. So I think the question for the panel is done now, and I think we can ask the rest of the audience to ask questions for the panel.
Yeah, thank you again for that interesting question and answer session from the panel. The question, one of the questions I have is in terms of cross domains, like when you're talking about discovery. Discovery is one of the things. Are any scientific experiments that we do? So if you want to discover something, or if you want to come to we talked about hypothesis and things like that. So there needs to be this change of reframing, actually, the problem itself in many sense. Like you go from one domain to another domain in one, like Nobel Prizes were won by people doing multiple levels of abstractions they go through from the quantum mechanics stage to actual doing the biological analysis kind of thing. So this whole notion, how good are the systems right now in doing these kinds of things, where you kind of grow across domains from one domain of quantum mechanics probably to another domain, the domain of biological enzyme reactions. So you have to kind of go through this, jump across these various domains. And how good are the current systems in terms of using this generative AI?
I can give you
And when are you going to go there?
Yeah, no, that's a great question. I can give you my few cents on this one. So obviously, this is one of the more challenging problems because we are dealing with very different scales, right? From quantum level scale to more of a macro level scale. We both in space and time, right? So the length of the reactions and are much slower on the biological level versus on the quantum level. And the other challenge is the degree of I would say predictability of those laws, right? So we feel a little bit more comfortable to put a heavy foot saying, okay, physics is physics. There are some conservation laws. We almost feel very comfortable to say they should strictly be honored, while in biology, we often have some processes that occur with some degree of stochasticity or maybe even with some chaotic behavior. And there is a very different degree in which we can expect to induce or deduce some hard coded laws on the biology side compared to, let's say, the physics side. I believe that Gen AI can help us to bridge that gap slowly. It will take a lot of time because we need to build a bridge after a bridge, right? We start with maybe with the more fundamental physical laws. We would build a bridge to chemistry, where that's the nearest, let's say, a science that where we can see how physics become, manifests itself in reactions and so forth. And then we'll have to take another step into biology. I don't know of any other simple way to do this sort of leap, but maybe some of the ideas that Jarvis mentioned about the composition can help us to even bridge that in a different way, right? So this is not a linear bridge. Maybe this is a bridge that requires bigger jumps.
What's the timeline here?
It's a question, what are your expectations in terms of fidelity, right? Because if your expectations are relatively modest, we are already there, right? We already employ Gen AI in biology, in chemistry, in physics. We get reasonable results. Some of them are useful, right? So when it comes to maybe the bottom line question, is it useful? Yes, we get some models that are useful. Are they consistent? Maybe not fully consistent from scale to scale. And this is where I believe that we need to bring that bridge, right? So we can come up with models that are phenomenological, they are not fully derivable, right? So this is where I put maybe the divide, right? We have models that are derivable, are things that we all feel very, very comfortable, right? We would start with a set of axioms and we deduce a new law that we say, okay, it is really completely dependent upon those axioms, and I feel very comfortable with what that model is. That will be much more challenging to get to. We do have models that are induced, right? We bring a lot of data, we bring some knowledge, and we try to make everything work together. I believe that this is more of a gradual process until we will be able to bring more and more of that knowledge and the data to tell us with higher level of fidelity how those processes in biology, for instance, are related to the fundamental, let's say, quantum mechanical processes.
So probably one possible methodology could be that domain foundational models, if one can concatenate them and one is allowed to change them, and you can tailor these to get the kinds of models you want, right? I mean, that would be a good way to do it for future.
Yes, one thing in the test. Yeah, one thing I think in the advancement of science is hypotheses are proposed and often proved to be wrong. And one wonders, in fact, their wrong hypotheses are hard to publish. And so that might point to a place where Gen AI could think about how wrong hypotheses would be developed within this framework as well, because we wouldn't want to be throwing out ideas that avoid dead ends in the advancement of science.
I can comment quickly if I mean. So I believe that there is a big question as for whether you find other viable hypotheses in the vicinity of one that is wrong, right? So if you think about it as maybe as some sort of geometrical space of hypotheses, are there, and we see that in combinatorial optimization and other domains, right, where we have a solution that is not optimal, right? Is there another solution that is optimal in the vicinity or not? And in some domains, you actually find that you may find one, right? So it's the fact that your hypothesis was wrong doesn't necessarily mean that you need to completely abandon the entire branch of exploration. You may be actually very close to something fantastic, amazing. In other problems, they seem to have a very I would say erratic underlying topology of how consistent or inconsistent such a hypothesis is with the data and the knowledge, and a search in the vicinity of such hypothesis will not really lead you to anything meaningful. And it's a good question. How do you characterize your hypotheses and the space in which they live in, right? Is it worthwhile for me to do a local exploration next to an incorrect hypothesis that apparently was not that bad because I arrived at that, so I had some guidance, or we should just go and complete the exploration.
And wrong hypotheses can be a constraint to avoid dead ends, and so it seems to me little thought to that might help.
Absolutely.
So I was just going to comment that it was a really kind of insightful thought with your question, and it kind of made me wonder how the performance of these models would be different right now if the literature contained a lot of these instances of false hypotheses, right? So the coin of the realm, so to speak, for us advancing science was always kind of hopefully positive kind of results that would build on a foundation. But we now see things like if you do image generation with, stable diffusion or whatever, there are negative prompts, right? So it's like, here's what I want, here's what I don't want. And I think that both sides of the coin are kind of equally valid in this context. And that's a really kind of cool idea.
Hi, thank you for the panel. I have a two-part question. One is the concept of the test bed itself. What are we testing? So if you look at the test bed, the way that these GPTs and all those are released every few months, what are they testing? What are we trying to test at what level? That's one thing. And second, the intersection of domain is where the actual innovations happen. From where I come from, energy, water, material nexus and the intersection between them. And then one of the biggest problem we are trying to solve is the energy for data centers. How AI is going to increase the energy implications for that. So energy for AI and AI for energy. So those are the two things. So if you want to develop such a test bed, and what is that we are trying to test? And can you ask ChatGPT to generate its own test bed? The reason I'm asking that is, if you're trying to benchmark something, most of the algorithms may work and show that it is working very good for that particular benchmark test. But if you want to do something much bigger in concept of a test bed, what are we trying to achieve in the test bed? So I didn't get the concept of what you mean by test bed in this. So just a clarification question.
So I can give you my understanding at least. So when we look into the scientific method in general, right, there are two possible ways we can go about that, let's say, arc between hypothesis generation and hypothesis testing. One is a deductive form, right? So you bring your knowledge, you articulate all the axioms and background knowledge that you have, you deductively derive a relation, and then the testing is really about making an experiment that will empirically validate that what you deduced is indeed correct, right? So that's one passage that we historically actually had many of those. In the recent days, we actually go in the opposite direction, right? So we take the data and we let the data drive, I think, as you said in your talk, and we induce from multiple instances a hypothesis. That hypothesis may or may not be consistent with the background theory, and then the testing is actually against the theory, right? So that's a completely different direction compared to deductive, where you go from the theory to the validation, to the empirical validation. You go from the data, you identify patterns, you then form some hypotheses, and then you do some validation against theory. Both arts are important and equally useful. I believe that it depends really how much knowledge you have, which is trusted in you, and how much machinery you have in order to deduce such hypotheses versus how much data you have in order to induce hypotheses that are meaningful. So to your question about doing that in the energy domain, I assume that the law of physics are relatively well established, right? So in a sense, you are standing on relatively firm ground when it comes to at least not complete, but relatively complete knowledge of the background theory. The challenge is typically maybe in the experimental validation. I don't know whether you do it fusion energy and you want to measure what is the yield of such system under million Celsius degrees and unbelievable pressures. It's challenging to even come up with a proposition as for what is the experimental design. How do you build the right platform and the right pedestal and all the elements that are needed in order to make an experiment that will provide you insight or meaningful understanding as for how correct was your deduced hypothesis. But I hope that I answered the right question. Maybe I didn't.
If you're talking about verification and validation, verification is about, are you doing things right? Validation is, are you doing the right thing? So the physics of the problem. When you're talking about data-driven approaches, whether it is for predictive or discriminative AI, there is no best practice. That is one of the biggest problems is generalizability and repeatability of these models. Where I sit, I get hundreds of proposals saying, I put sensors, collected data, here is the prediction. And then put sensors, collected data, put some. So there's no way that we can generalize that, repeat it and there's no best practice of how you trained it, what is the verification, what do you mean by validation there? What are we testing? So those are the questions I am trying to get at, because we have developed a lot of test beds at DOE at various labs. And each of them, when we develop the test bed architecture, we go with a clear idea of what are we testing, why do we test, and who is validating it? Is it human in the loop, or it is validating itself? So those are the questions I was trying to
Right. So obviously what goes into the test bed is like what domains are considered, what types of questions are featured, have pretty big downstream consequences for what the focus is on. And I would imagine there's kind of this balance between practical concerns such as readiness for a certain domain to provide easy to work with data and questions, and then also probably something like the societal impact of what progress could mean. Could you comment on what goes into those decisions for kind of recruiting domains into test beds, and also how you deal with the varying degrees of say, fragmentation in a certain domain that might make practical uptake in early days quite a bit more challenging, despite having a lot of value if progress is made?
So in one of the proposals NSF funded on the test bed, I think it was to Cornell for agriculture, if I'm not mistaken. And I think the idea here is they had a bunch of issues in which the agricultural scientists needed to address, and the main concern, the main reason to build this test bed, or this is just a pre-proposal for saying what the test bed should be. Anyhow, the main reason to fund this was to say that in a realistic situation where the agricultural research and production is going on, what are the various issues that needs to be addressed, and can this test bed emulate those circumstances? That was one of the main concerns. And then the next concerns is what are the algorithmic issues, what are the systems issues in order to realize those goals.
Hi, I have a question. I'm Jigyasa. I'm a PhD student here. So to tackle some complex problems, we have so many methods to tackle. So to tackle the small parts of that complex problem, we might have a variety of methods which are like completely different from each other. But sometimes these methods who are handling different parts of that big problem become so intertwined that it's difficult to gauge which method is contributing towards the like improvement at the end results. So especially when you don't know what to expect at an intermediate state, and also maybe for the sake of compatibility, you have to change multiple methods at a time. So I understand that this is a very general question and it depends from problem to problem how to handle this. But if you could share some thoughts about it. And a follow-up question to this is that how important is it to have these reports of individual method performances for the community?
Maybe that also relate to the previous two questions. So I'll try to provide a useful answer here. In other domains in AI, we typically have benchmarks, right? And these benchmarks are well-defined set of problems and data sets that we can bring our best method and see how it pars against other propositions, and that seemed to be a relatively well-defined yardstick that we can do all those comparisons and feel relatively comfortable about it. When it comes to the scientific domain, we typically have problems that have a stronger sense of realism, right? So the data is real. It's not some artificial benchmark that somebody created in the lab, right? We have a greater diversity of problems that we tackle, right? So it's hard to settle upon, here are like 5 problems that we all agree that this is what we all do together, and if we score best on those one, we are doing well. And maybe the other question is indeed, how do we characterize the methods we use, to your point, right? In terms of their contribution to uncertainty, to errors, to other either positive or negative artifacts, implications of what we are trying to do. And one way to try to address it is a community effort, right? If we try to come up with a unified set of even a language, right? So how do we articulate the theory in one unified language? We can use systems like Lean from Microsoft Coq. There are other Isabel, other formal methods. But if we agree as a community, let's all use one of them and articulate all the background theory in that language, at least we have one consistent place where we know that at least the definition of the background theory is one, right? So you will not have to translate from one problem to another and say, oh, you changed the name of the variable, and therefore, I didn't even understand what you were doing, but both of us were trying to do conservation of energy, but it was not obvious that we were trying to address that. So on the theory side, I believe that it is relatively maybe more amendable. On the data side, I guess we will have to build up some hierarchy of different problems and understand what each data set attend to. And if we bring a little bit of order and discipline into doing that, maybe we have a hope to learn from each other, because otherwise each of us is doing its own point effort, get a paper published, maybe do something locally meaningful, but it doesn't scale to anything beyond that. The moment we have some unified repository of models, of theory, of data that as a unified format, right? There is some discipline. Potentially, we can take that to the next level and build upon each other's, also to your point, mistakes and successes.
Yeah, so certainly Lior's, points are, quite good, really, so in this case, focused on, it seemed like focused on the data, the algorithms that say things like accuracy, but then there are domain-specific considerations like, what is the potential payoff? Do you need a quick answer and let's say a quick and dirty answer is good enough, or do you really need to take more time to get a more accurate answer? Let's say, do you have sufficient compute horsepower, disk storage, whatever it may be, for your particular problem? Just it calls to mind, to make it a little bit concrete, we have looked at in aviation safety, let's say radar track data, but only when the radar track data look anomalous do we bother to pull up voice recordings, because it's the vast majority of the time nothing interesting is going on, so it's not worth hogging all that disk space for those recordings. But of course, that means the voice recordings that you're pulling up are very skewed towards the cases where something abnormal is happening. So you have to account for that in your method. And so you have to deal with all those practicalities as well, which, as you said, is very domain specific.
Yeah. We're out of time, but I think what was the most interesting part was the set of questions people ask. I think at this early stage in GenAI, we don't have to have the answers necessarily, but we should be asking the questions, and the right set of questions is what's going to drive the field, right? So it's perfectly fine for us to stumble on the answers. It's just that we just have to formulate and continue to keep formulating questions and challenge us ourselves. So I would say let's thank the panel. And we're going to break for lunch, and we'll be back here at 1 o'clock sharp. And I think Paul Hansen is going to moderate the next panel. Thank you.